Okay, now we are on time to start, and the first talk today will be by Gabriele Conti on the canonical equivalence of the Jordan and Einstein frames. So thank you very much, Gabriele.
Thank you to the organizer for the possibility of talk about my research. It's been a while that I'm working on this subject. And you have heard this morning by Wetterich the importance of passing from the Einstein frame to the Jordan frame. So it's a sort of complement of the talk we have heard this morning for the part of Jordan and the Einstein frame. Essentially, does not work. Okay. What is the machinery about? There is an old paper by Dicke that dates back to 1962 that says that essential physical quantities are defined modulo definition of unit of measurement. I mean that if I have the proton mass here and its value is defined according to its unit of measurement. If I rescale the unit of measurement by quantity in a natural unit of lambda to -1, the new measurement of the measure of the proton would be lambda -1, the old measure, in such a way that this ratio will remain the same. Next one, okay, works now. And so if I have the proper length here, and I rescale the unit of measurement, the proper length is rescaled by factor lambda, in such a way that since the proper length is related to metric coefficient by square root, the metric coefficient will be rescaled by factor lambda square. So if in physics things are defined modulo redefinition of unit of measurement, physics should be invariant under conformal transformation. It's written here on the metric coefficient. So the starting frame is called Jordan frame. The other frame you heard this morning is called Einstein frame. Now, what Dicke would say in the original paper would say that the observables should be the same in the two frames and are related by factors that are the scale factor of the conformal transformation according to the what is called the natural length with which to their dimension in natural length. This means that the mass of proton in the Jordan frame, in the Einstein frame, is related to the mass of proton the mass of proton in the Einstein frame is related to the mass of proton in the Jordan frame by a factor that is the inverse of the square root of the conformal factor. So you can compute things in the Einstein frame and the Jordan frame, and you have to relate by things that are connected to the conformal factor. Okay, this is the old way of thinking. What usually people do is they write, for example, a scalar tensor T of gravity with Gibbons, Hawking, York boundary term, and they transform from the Jordan frame to the Einstein frame. And they obtain a theory of gravity that is Einstein general relativity plus a scalar field. The guess is that if I have a solution of the equation of motion in the Jordan frame, the transformed one should be also a solution in the Einstein frame. So this is true, from what I know, in Hamiltonian formalism, only if this transformation is an Hamiltonian canonical transformation. So I try to show if this transformation is real Hamiltonian canonical. What is the problem? For example, people start for Brandstücke theory. For example, Garay and Grassi-Abellito, they say that this transformation, they assume is canonical, and they do the constraint analysis of Einstein general relativity. They do the constraint analysis of Brandstücke theory in the Einstein frame because it's simple because reduced to Einstein general relativity. And they say that it's the same. But this is true only if the transformation is Hamiltonian canonical. You have not proved that it's Hamiltonian canonical. And the same here with these people, Derwels and Under yourself. In this PRD, they assume that transformation is canonical because they check that all these Poisson bracket are 0, but they didn't check the Poisson bracket related to the lapse, because they say that the lapse is only a Lagrange multiplier, so you don't need to calculate. But you need to calculate the lapse, because if you calculate the lapse with the transformation well written from the Einstein to the Jordan frame in Hamiltonian formulas, you see that the transformation is not canonical. Simple. So you do the right calculation separately in the Einstein frame and the Jordan frame, and you find that really the Einstein geometrodynamics, I mean the constraint algebra, in the Einstein frame and the Jordan frame, in the case of Brans-Dicke theory omega different by -3/2, this constraint algebra is the same. But the same thing does not apply in the limiting case omega equal -3/2, because you have a constraint algebra in the Jordan frame that is completely different by the constraint algebra in the Einstein frame. So really, this shows that the transformation, strictly speaking, on the extended phase, it's not canonical. But there is a canonical. Sorry, this is another example of how things works. Suppose you have a Brans-Dicke theory in which you use a mini superspace model of a flat Friedman Robertson-Walker metric. You put inside the action, you derive the Lagrangian in the Jordan frame, and you do the same thing. You use the transformation from the Jordan frame to the Einstein frame and calculate the Hamiltonian in the Einstein frame. You derive the equation of motion, and you derive the equation of motion here. And after you do this exercise, you pass from the equation of motion in the Einstein frame to the equation of the motion in the Jordan frame. You retransform twice, and you see that things are almost the same, except the equation for the lapse, that cannot be reduced to the equation of the lapse for the in the original Jordan frame. So things look different. So what is the strategy to show that you can have a canonical transformation? The strategy is the gauge fixing. You gauge fix the lapse and the shift in the Jordan frame. This implies a gauge fixing in the Einstein frame. So in this way, you implement this gauge fixing as a secondary constraint. So in this way, this constraint and this constraint, together with the primary first class constraint, make this primary first class constraint second class. You reduce this. You reduce the second class constraint introducing Dirac brackets, and this proves that you calculate the equation of motion with the Dirac brackets. Once you calculate the equation of motion with the Dirac brackets, you find that the transformation is canonical using Dirac brackets and solving the second class constraint. So there is a canonical transformation, but you have to gauge fix the lapse and the shift that are really variable, but once you really gauge fix them and reduce and solve the constraint, you find the canonical transformation. But does it mean that the canonical transformation, since we have found the canonical transformation, the two systems are physically equivalent, Jordan-Einstein frame? In principle, not. Why? Because there is the example of the harmonic oscillator. In the harmonic oscillator, there is a canonical transformation that maps the harmonic oscillation to a free particle. And this is a canonical transformation, but the free particle and the harmonic oscillation are two different systems. And furthermore, there is this other transformation that is the anti-gravity transformation. This is a canonical transformation for the Brans-Dicke theory, but it's a transformation that maps it's a transformation in which that represents space-time. It's a transformation in which you do conformal transformation only on the three surfaces. So it represents space-time like this, that are space-time that are typical in which as the factor lambda increases, the construction squeezes and becomes smaller and smaller. And so this, in the limit, the limiting velocity, the corresponding of the velocity of light goes to 0. So you have this thing that you start from the Jordan frame. If the transformation from the Jordan, if the canonical transformation is a transformation that is also physical, the Jordan frame should be equivalent to a frame that is the Einstein frame in which the cone structure is preserved, and also to another frame that we call anti-gravity frame in which the cone structure squeezes. So it's impossible. So we have to admit for this case that the transformation from the Jordan to Einstein frame, it's not really a transformation that map a physical system to another equivalent physical system, but it's only a mathematical transformation that can be used to solve your mathematical problem in a system in which the mathematics is simpler. So what I'm finished. Well, the transformation from the Jordan to the Einstein frame in the extended excess phase is not an Hamiltonian canonical transformation. A Jordan frame, Einstein frame, gauge fixing Hamiltonian canonical transformation do exist, but we have to gauge fix the lapse and the shift, and you have to reduce the constraint, eliminate the lapse and the shift with the Dirac procedures of introducing Dirac bracket. The very fact, this very fact does not mean that the two frames are physically equivalent. It still remains to be proved that the observable in the two frames, Jordan frame and Einstein frame, will give the same result. Thank you.
Thank you, Gabriele, for the nice talk. We have time for questions. Super.
Yeah.
Well, my question, first I would like to say that I liked the talk very much. I think it is interesting to develop more these ideas. Certainly it can be applied to other theories, and the question is the following. Well, you considered Brans-Dicke, but there are other scalar tensor gravities. For example, gravitational Chern-Simons. I am speaking about gravitational Chern-Simons because I had some experience with it. Whether it is possible to follow this way, apply this methodology for gravitational Chern-Simons, four-dimensional, of course.
My question would be, is like a scalar tensor theory?
Yeah, gravitational Chern-Simons in four dimensions.
I think you can apply this technique to your example as well. There would be no problem.
Okay, one more question. Meanwhile, could people please move in or let people sit as well on the...
Thanks for the talk. So I was wondering about the physical motivation behind this gauge fiction, like you were talking about.
You have seen this morning in the talk of Christoph Wetterich that is there, that he passed from the Jordan frame to the Einstein frame.
Yeah.
And they assume that the transformation does not have any consequence. In my opinion, the transformation is only a mathematical transformation. The physics, as I have shown in the example of the harmonic oscillator, could change completely. And also, we have canonical transformation from the Jordan frame to another frame, it is anti-gravity frame, that modify the structure of the cone structure. So I doubt that the physics is the same, but this is my opinion.
That's something for the ice and coffee break. So please, again, let the people move in and sit if they want. And we prepare for the next speaker then. Thank you. So the next speaker will be Andrew Görlich on the impact of matter fields on quantum geometry.
I'd like to discuss the effect of matter fields on quantum geometry in an approach called causal Demka triangulations. So I will start with a very short introduction. What it is. Causal Demka triangulations is a background-independent and deformatism invariant and also non-perturbative approach to quantum gravity, and it provides a lattice regularization of the formal gravitational path integral. So it replaces it with a sum over triangulations. They are four-dimensional and built of four simplices, which are generalizations of triangles to higher dimensions. And there are some assumptions, like we introduce global proper time foliation. It's a discrete model, so we enumerate slices with integer times. And this allows us also to define an observable volume profile, which is the volume of a slice defined as the number of the trahedra in this slice. And we also control the topology both of the spatial slices and the global topology. And we can use Monte Carlo techniques because of the foliation. The weak rotation is well defined, and we end up with a statistical model. And we use Monte Carlo techniques to generate configurations according to this probability, and we can measure expectation values of some observables, the one that I mentioned, or study the properties of typical configurations. Even though our building blocks are four-dimensional, the triangulation or a geometry that it represents is nothing like a regular smooth geometry. Here I will focus on a toroidal topology, and it looks much more fractal, more like this picture that is just a visualization illustration on the right-hand side. And now we introduce dynamical scalar fields. Dynamical, it means that they back react on the geometry. So we add the action for the scalar fields to the action that is used to generate those configurations. And we'll take a free massless scalar field. But those scalar fields, they will take values on a circle with circumference delta. And this circumference is a quite important parameter here. And we require that a given scalar field winds exactly once around the circle in given direction, depending how we define it. And we use a discretized version of this action. It consists of a quantum part and a classical part. This may be more technical, but we see that the classical part scales as delta squared in the action. So this suggests that when the circumference grows, the effect of the matter fields will also grow. And we'll start our discussion with just a single dynamical field that winds once around the target space when we go along a non-contractible loop in the time direction. And we can see that for small volumes, for small circumferences, delta, there is no change. And if we look at the volume profile, so the average number of the trahedra in given slice, there is a drastic change when we cross some value of this delta. We get the cosine function of this volume profile, and it's a pinched profile in the sense that it goes to zero, almost to zero, because it's not possible to go exactly to zero because of discreteness, almost to zero at some points. And in this region, the field changes abruptly as much as possible, while here it is changing slower. This will be also visible later. Now, we can explain this cosine behavior very well with the multiple space model, where we assume spatial homogeneity and isotropy, both of the metric and the scalar field. And one of the solutions is a cosine function for the volume profile, and it works very well. So if we have a single field, there's a pinching in the direction in which the field winds. Now we'll go to more fields, but let me make some introduction for the pictures I will show later. So as I said, the action that we use that govern the fluctuations of this scalar field, it consists of a quantum part and a classical part. And the quantum part can be integrated out. L is the Laplacian, discrete Laplacian for this triangulation, and it's basically negligible. But the classical part, so the field fluctuates around a classical solution, and the classical part is the value of the action for this classical solution that winds also around the circle of circumference delta. And that if we take the dependence on delta in front of this parameter here, this classical part of the action, it depends as delta squared times a function that depends on the triangulation. And if this part becomes important and it dominates the action, then it will impact the triangulations that contribute mostly to the path integral when such scalar fields are present. And indeed, we observe this for the single scalar field, that for small delta, there's no change. It behaves more or less in the same way as if there was no field. But for large delta, the matter part of the action dominates, and the total we have the preferred configurations are those who are pinched to a very small volume in some region. And now to visualize triangulations and field configurations, we now will reintroduce classical scalar fields. That's maybe technical detail. So we will assign the value of those four fields, phi x and up to phi t, to each four simplex. So we can think of the field as living in the center of a simplex. We have these four fields. Phi x winds around the target space when we go along the x direction. And on the next plots or images, a single pixel will denote a single four simplex. And dense regions will form fibers, and they will correspond to evolving outgrowths that I have shown on one of the first slides. So we start with three dynamical scalar fields that wind in the spatial directions. This is a projection only on the phi t field, which we introduce as a classical field only for the purpose of visualization. And on the y-axis we have phi x. And here the circumference is 0, but you can think of it as a very small circumference, so the field is allowed to fluctuate still. So there is still the effect of quantum fluctuation of the field on the geometry, but this is basically negligible. And this plot here looks very similar for if you take just a typical configuration without any dynamical scalar fields. You can always introduce the classical scalar fields on top of an existing triangulation only to visualize it. So we see here there are some fibers with some elongation in time, and they denote an outgrowth that also evolves in time. And now let's see what happens when we change this delta parameter, the circumference of the target circle for the scalar field. And we see that dense regions start to form. And we can expect, observing my previous results for a single scalar field, that it will localize, it will pinch in this direction where it winds. So phi x, for example, is one of the directions. And it should localize for some value. And this is indeed what happens. When I increase the delta parameter, the simplices using the coordinates defined by those scalar fields, they tend to localize or condense around some value. But what's, and this we explained already earlier, what's maybe more strange is that once you cross some value, it also, the volume profile start to change. Now we don't have a field that winds in the t direction, but the volume profile measured in the time direction does change. And it then collapses to a single point in the field coordinates, which means that we have one large outgrow because one large outgrow will be visible as a very dense cloud of points. So if we look at the region where this change happens in the volume profile, it is now given by a cosine cube function. So here again, it's a volume profile on this axis. T is the original time foliation, and the volume profile, the average volume profile, behaves like a cosine cube function. Previously, we had a cosine function. Here we have a cosine cube function, which is exactly this what we observe also for a spherical spatial topology. So let me repeat that here, the topology of the triangulation or of the space-time is toroidal. Both of the first topology of a space is T3, but we get a behavior typical for spherical spatial topology. And we can also explain it using the mini superspace model. So first we observe, as I have shown before, that if you introduce a scalar field that winds in a given direction, there is a pinching in this direction. So like we start with the torus, but there is a pinching, let's say, at the end of the torus, and it effectively becomes a sphere. Of course, exactly by construction in our numerical simulations, it is a torus, but effectively the bulk of the volume is like has a topology of a sphere, it's spherical, and it starts as single slice starts to look like that. That there is a small area which with the genius with the hole, and the bulk of the volume is in the looks like a sphere. And we know that if the topology of the space is spherical, we have a curvature term, and this explains this bubble-like behavior and this cosine third function. So that the procedure or the effect is twofold. First, there's a pinching in the direction where the scalar field winds, and then the effective change of the topology of space enforces this blob behavior. Okay, so I should finish now. I will just say that we have shown that introducing dynamical scalar fields, it changes an effective topology of space and also space-time, depending on the delta parameter, which is the circumference of the target space of the field. Thank you.
Thank you very much. Questions? So maybe a short question. What is the crucial difference with these holes? So ball and then donut or brezel, how would that?
What's the difference on this plot? Well, the region where you have this hole is now much smaller, and the main volume, if you subtract or cut it out, then the main volume will be like a sphere with a pinch only.
Okay, so let's thank the speaker again. Okay, you get the microphone over here. And the next speaker will be Simon Langenscheidt on isometric boundary maps in quantum gravity entanglement graphs. Thank you.
Okay. Can you hear me? Can you hear me? All right, so I'd like to thank the organizers for letting me speak about joint work with Eugenia Colafranceschi and Daniela Oriti. Wait. There we go. Okay, so as many of you will know to some degree, there are certain motivations in quantum gravity to believe that we have a kind of holographic principle that describes certain aspects of quantum gravity. This comes from an example from ADS-CFT, scattering amplitudes in celestial holography, from quasi-local holography in corner symmetries, but more modestly from black hole information arguments. Now, what we were trying to do was to figure out how much this applies in a discrete space context. So in a more general setting, we were looking at what we call entanglement graphs, describing discrete spaces built out of chunks, and looking at bounded regions described by these sorts of structures. And because entanglement and information transport play a central role in the CFT side of the ADS-CFT correspondence, we also wanted to focus directly on how this influences the side in our discrete models. Now, we did this using random tensor network techniques. I will get into this a little bit more, but the main point is that we fixed certain structures on our quantum gravity states, describing space itself, and then randomize over the rest in order to make typicality statements. To begin, what do we understand by an entanglement graph? What I want you to take away with as an image is a model of a space which is built from polyhedra, which are loosely glued together. We can dualize this picture by setting on each polyhedron a vertex of a graph, and the faces on which they are glued together we realize as links. So a typical example or realization of this would be spin networks as found in quantum gravity approaches like LQG or group field theory, in which you decorate these graphs by geometric data, which can be group elements which rotate local frames from one polyhedron into another, or it could also be area and volume values for links and nodes of the graph, respectively. Now, the slogan entanglement equals connectivity or gluing can be made very precise in this context. What I want you to think of is two of these polyhedra with associated Hilbert spaces to each of their faces. In this case, what we want is an L2 of G. So we have a wave function depending on a group element on each side. And these group elements, we will, and these wave functions, we will make a right translation invariant, which is a special case of the general construction that we take the two Hilbert spaces on each side and we project them on a maximally entangled state. Maximal entanglement means that they now share the same data on each side, which allows us to identify the data into a single copy. So due to right invariance of such a wave function here, we have now a wave function which depends only on a single group element, which describes a link that connects the two polyhedra. So the way we will work with these entanglement graphs is that we construct all of the full set of them by taking vertex states and then applying a bunch of projection operators in the pattern of a graph that we are interested in. Now, this is what describes a class of tensor network states known as projected entangled pair states. That's some terminology, but in essence, it's what I described here. It's just applying a number of projectors. Now, for some context in previous work, we used techniques that were established in the random tensor community, which studied ADS-CFT in a discrete context and found a lot of properties similar to the continuum story. But also our group and collaborators, Goffredo Kirko, have talks tomorrow, which are also on this topic, and I highly recommend you check that out. Now, the gist of the story is in this discrete setting, you can establish similar quantities and relations like the Ryo-Takayanagi formula, but in a more controlled setting where you have a clear sense of what is entangled to what, because these graphs directly tell you which side is entangled to which due to maximal entanglement. And also we could tell some criteria for when these graphs allow you to define holographic mappings. More precisely, the work I want to focus on extended all of this work to superpositions of different entanglement graphs, where the previous techniques of Haydn and others did not apply. What we needed to do as a main technical thing was to calculate the entropy of some bulk regions in this graph, which in usual tensor networks is straightforward, but we needed to find some other techniques to do that. We did this in an average, so not of a single state, but the average over a class of states. So we did pick a number of random states and then projected them using these maximal entanglers into a certain entanglement pattern, and then calculated an average over the vertex states. So using some tricks from the literature, this can be mapped. So the quantity that we want to calculate can be mapped into the partition sum of an Ising model, which lives on the same graph that we started from. But in our superposition case, this partition sum is actually itself a weighted sum of smaller partition functions, with the Ising Hamiltonians depending on the areas, on the link labels that we put on the graph we started from. So using this technical stuff, we can ask some more interesting questions about holography, because entropies are nice, but they're not holography themselves. So what holography itself could be is that we have some mapping between Hilbert spaces or algebras of operators. And the issue in our case was that the Hilbert space that you see at the top does not really factorize between bulk and boundary spaces. So I here stands for input, and V is a set of output spaces. And because this does not factorize, there's no natural notion of what the input algebra is and what the output algebra is. So figuring this out was a central issue, but using some techniques from quantum information, we could find an appropriate notion of entropy in the case where you don't have factorization. And also we could find that the classical Choi map from the state operator correspondence allows us to take a state of quantum geometry and define a mapping from it, which takes a bulk operator and gives us an output operator, a bulk operator that lives on a boundary. And actually, under certain conditions, just calculating some entropies is enough to show that this map, the super operator, is an isometry between operator spaces. And this really is a stronger notion of holography. So, for some results, we found that, of course, there must be some condition on the geometry in order to have these isometric conditions. One of them is really that in a superposition, if the geometry of the state we're describing, that we're superposing with others, is relatively large, then the weight in the superposition must be relatively small. So there's a bit of there's a product formula that must be fulfilled in each sector. The concrete cases in which this holds are still under investigation, but the general formula is known. Now, for some more geometrical properties of these states, we looked at something which was inspired from canonical GR. We looked at area expectation values of a state where one half of the boundary is mapped isometrically into the other half. And in these states, we can very easily evaluate the expectation value of the area, which of the region C, which is the one which we use as input. And it turns out to just be related to the mean area of all of the constituents that we put in a superposition. What's more interesting, perhaps, is that in these isometric states, or states that give rise to isometries, we find that there's non-vanishing uncertainty in the area. So they cannot describe semi-classical states. Now, as a summary overall, we studied bounded regions of space in an entanglement graph setting, and used random tensor network techniques in order to study when these states can give rise to isometric or holographic maps from boundary to boundary or from bulk to boundary. And we found conditions and geometric implications for these states when they actually do have isometric behavior. Now, there's still a lot of stuff we want to do. More explicitly, we want to go beyond the limitations we had to impose. One of them is that we had to limit ourselves to relatively large areas, which we may circumvent by going to numerics. But we would also like to have some more geometric control over what these isometric conditions imply. But also, of course, there's things like having dynamical behavior of these states, because so far what we looked at was just kinematical statements. And of course, given that this is directly related to holography and inspired by work in ADS-CFT, we would like to connect it more directly and perhaps establish some kind of direct ADS-CFT correspondence in the context of entanglement graphs and spin networks. So, thank you.
Thank you very much. So we're good in time. Questions? Don't be shy. Okay, a short question maybe on this equation 11, for example. You had this approximately. Is it approximately 4/3 or it's approximately linear in AC? So what is approximated?
So the setting in which this was derived is that you take a superposition of geometries which are as close to each other as possible. So what I wanted to approximate was, okay, if you have a single state in a superposition, no superposition really, no superposition of different spin labels or area labels, then the expectation value is sharp. So there's nothing you have to calculate. So rather the opposite case is you superpose as many different geometries as possible, and then you find this limit in the case where you superpose as many as possible. And then you have to take the mean area of all of the expectation values from the stuff you superposed, and it gives you this prefactor.
Okay, thank you. No further questions, so let's thank the speaker again. And we prepare for the next speaker, Ignacio Reyes.
Okay, thank you. Yeah, I'm Ignacio. I'm a postdoc at Amsterdam. Thank you. And I would also like to thank the organizers for the opportunity to talk here. So I'm going to tell you about something that should be out very, very soon. And it's an application of quantum field theory to the problem of the stability of stars. So let me start with a very simple observation that probably everyone in this room would agree with, which is related to the Planck scale. So if you start with classical general relativity with matter, you realize that the stress tensor, its components, are proportional to the curvature. The coefficient, the factor of proportionality, is G Newton. Now, if you introduce now quantum corrections to this matter or other fields, what you generically find, this is very hard computations to do, But after you renormalize, what you typically find is that the expectation value of the renormalized stress tensor scales as the square of the curvature. And in that case, the proportionality factor is h bar. So then when you ask the question, well, when do these components, so the classical components, become of the same order as the quantum components, you immediately realize, because of what I just said, that this only happens when the radius of curvature is of the order of the Planck scale. Or in other words, if the density is close to the Planck density. So therefore, we can neglect the quantum effects due to the curvature of spacetime if we're below the Planck scale. Now, this simplicity of this argument does not prevent it from being completely wrong. And I'm going to explain you why. And it's very easy to see it. So I'm going to derive this using the trace anomaly. So what does this mean? If you do quantum field, if you study quantum fields coupled to gauge fields, in this particular case, general relativity, generically anomalies appear. In this case, we're doing quantum field theory in curved spacetime. What does this mean? So the total stress tensor contains two contributions. One is has this index m here, which refers to a possible mass term. So this contains the contributions that break conformal symmetry already at the classical level and of course at the quantum level as well. And they do not depend explicitly on the metric. This is something that you're supposed to solve. You put it into the Einstein equation and you solve the equation. On the other hand, there's another contribution, which in this case is the anomaly. And it is explicitly dependent on the curvatures. It grows quadratically with the curvatures, as I said before. Now, in 3+1 dimensions, the Weyl conformal or trace anomaly is the statement that this last contribution, the anomalous contribution, is completely fixed, and it depends. It's given by this formula, where the first term is the square of the Weyl tensor, and the second term E is the Euler density or the Chern-Gauss-Bonnet density that appears in the Chern-Gauss-Bonnet theorem. So it's the thing that if you integrate it over the manifold gives you the Euler characteristic. It's a topological term. Now there are two coefficients associated. These are two central charges. They're very well understood. I'm not going to focus on them. They're not going to be important. The thing that will be important is that their signs are completely fixed. So given a theory, these coefficients depend on the Lagrangian. If you give me a Lagrangian, we know what these coefficients are. Okay, so that's the conformal anomaly. So I'm going to make a set of assumptions and then show you what the result is of a very trivial calculation. So I'm going to assume that if we're much below the Planck density, so still the Planck scale is very far away, first of all, I assume that the semi-classical approximation is the description of the system. Okay, and that means that the metric is still classical, and the stress tensor has these two components, as I said before. Assumption number 2 is that is something about the behavior of the equation of state of the matter at high energies. And the assumption is that matter at very high energies, still below the Planck scale, looks conformal at leading order. And I expect this to be true of essentially all theories. So what does this mean in practice? It means that if you take the trace of the matter component, these two terms, for an exactly conformal field theory, these are going to vanish if you put the mass to 0. But the statement is that this thing scales. This doesn't need to vanish exactly because we're approaching a conformal fixed point. But the point is that this has to scale with some power that is smaller than 1. So this quantity over here scales with the density, but in a way that is slower than linear scaling. Finally, there's this m here, which is whenever you just write the equation of state of a system, there's going to be some mass scale that appears. I'm just calling that m, and I'm going to tell you what it is in an example. The last assumption is that the individual components, if you compare component by component of the anomalous stress tensor, they are all subleading with respect to the matter, the fluid contributions. So what do we get out of this? So now consider taking the trace of the semi-classical Einstein equations. In 4 dimensions, the left-hand side just gives the Ricci scalar. And on the other hand side, we're going to have the sum of these two traces. But we already know what these two traces are. That's what I told you in the last 2 slides, right? So this, the matter contribution is exactly what I just showed. So it scales slower than a linear power. That's because we're approaching, the theory is looking more and more conformal. And on the other hand, we have the anomalous contribution. Now, if you simply use the assumptions that I just showed you, it's an absolutely trivial exercise to realize that if you take now the trace of the Einstein equations, you see on the right-hand side, you have the contribution of the matter, of the fluid, plus the contribution of the anomaly. I told you this scales quadratically with the densities as usual. So now when I ask the question, not of when do component by component these two objects become of the same order, but rather when do the traces of these objects become the same order, the answer is not the Planck scale, but rather this thing over here. So what I'm asking is, when does this contribution, the anomalous contribution, the quantum contribution, become large enough such that it has an impact on the Ricci scalar? So I essentially put this to 0. This is this value over here. So the Ricci scalar, what does this thing do? At low densities, this thing scales as the linear term. That's standard, let's say, classical physics. But at some point, the anomaly kicks in, the Ricci scalar, and because the sign is fixed, that's completely fixed by the trace anomaly in 4 dimensions. You cannot choose the sign. You cannot choose the coefficients. This means that eventually the Ricci scalar reaches a maximum, goes to 0, and changes sign. And the point where it changes sign is given by this density over here that I just got from this equation. And what you'll see is that the critical density where the anomaly becomes macroscopic is not the Planck scale, but it's the Planck scale multiplied by this ratio over here. And it's the ratio of the mass scale that appeared in the equation of state divided by the Planck mass to a certain power that depends on alpha. That was the number that appeared in the equation of state. So let me consider the most important, or I think the most interesting example, if I'm doing astrophysics. If I just take the Fermi gas at 0 temperature, I'm just telling you what the answer is. Alpha, that example corresponds to alpha equals 1/2. The mass appearing in the equation of state is the mass of the electron. If you evaluate this density, it's 30 orders of magnitude below the Planck scale. So, why is this relevant? A very simple application is to consider the problem of degenerates or compact stars. So if you open the Bible on compact objects, there are 2 big results in this field. One is coming from the 1930s, that's the theory of degenerate stars, which only uses the Pauli exclusion principle. The anomaly was not even known by this time. So of course, they cannot take it into account. The second important result is not related to the stability as is the first, but rather to the existence of static solutions, and that's due to Buchthal in 1959. So what does Buchthal theorem tell us? Well, it tells us that if we take a static spherically symmetric perfect fluid, and you want to solve the Einstein's equations, without solving them and without assuming anything about the equation of state, you can only assuming that the density is positive, that it is non-decreasing outwards, and that the Einstein equations hold, you can show that there's a bound on the ratio. If you have a sphere of mass m and radius r, there's a bound on the compactness. And that lies a finite distance away from the black hole, from the Schwarzschild radius. So this is happening much before. And what's happening in the Buchthal limit is that the central redshift is going to infinity. So the metric is degenerating at the center. And that's the limit that I'm interested in. So finally, the question I wanted to understand is how do you assess the stability of an object, say, close to the Buchthal limit? So a very compact star. Now taking into account what I just told you about the anomaly. So to do that, a very simple thing you can do is to just study scalar perturbations at the linearized level. You can, as usual, rewrite this thing as a Schrodinger equation by changing coordinates. And the point is what this effective potential that appears in the Schrodinger equation is. So what happens is the following. If you, say, consider the L equals 0 sector to make it easy, if you neglect the anomaly, or in other words, at densities below this critical density where the anomaly becomes important, this potential over here, I'm just telling you the result, this potential over here, its minimum is negative. That simply comes out of the wave equation. Okay, this is not obvious from this calculation, but that's just what you get. the fact that the minimum of this potential is negative implies that it hosts bound states that are unstable because omega squared is negative. So these are exponentially growing modes. This means that the star is unstable. Now what happens when the density at the center of the star reaches this critical density when the anomaly becomes important? The Ricci scalar changes sign, and the Ricci scalar is what controls the location of the minimum. So at that point, the potential changes sign, the bound states disappear, and this object regains stability under these perturbations. So in conclusion, we saw that the effects of the trace anomaly become macroscopic not at the Planck scale, but much before that. How much before? Well, it depends on two parameters that appear in the equation of state. For an electron, say, this is 30 orders of magnitude before the Planck scale. And if you study scalar perturbations of stars close to the Buchtal limit where this effect is important, then you realize that objects that you would have thought that are unstable under these kind of perturbations actually become stable because of the effect that I just described. So as an outlook, I only considered spin 0 perturbations, but of course the interesting thing is to look at, say, spinor or spin 1/2 or spin 2 gravitational perturbations, and to understand how this all relate to the dynamical problem of gravitational collapse. Thank you.
Thank you, Nasir, for the interesting talk. I will run only on the right side. If you hand the microphone to the left, I'm happy. So 1, 2, 3 questions.
I found that rather convincing, but I have a simple question. What is the quantitative size? If I look for a neutron star, for example, or things like that, how much is the change that you get in addition, that you gain, in order to have something stable instead of unstable? If it's only a change in mass of let's say a few per mil or something like that.
Yeah,
it's theoretically interesting, but in practice it does not. So, just a number on
it depends
how big is the effect.
Yeah, well, I think that's the wrong, or it's not exactly the correct question, but maybe let me try to answer it in a slightly different way. Okay, sorry. So let me consider this case, for example. If I take a star made of degenerate electrons, say, this effect, well, the mass of the neutron is basically the same as the mass of the electron for these effects, so it doesn't matter. So you could consider a neutron star, for example. Now, the density of a neutron star is something like 40 orders of magnitude below this number. So this physics has nothing to do with the Chandrasekhar and Tolman-Oppenheimer-Volkoff limits. This is a physics that appears at a wildly higher scale. The effect that I was talking about today doesn't correct in any way the results from the 1930s. This is something that appears at an incredibly higher, so this is 30 orders of magnitude below the Planck scale.
It's a force power, so if you think in
yes.
scales, it's just
exactly.
like that. It's not so much.
Right, but this means, that this physics this can in no way be considered a correction to the theory of degenerate stars. Yeah.
What I wanted to get out.
Yeah.
It's an effect that is, once you reach really linear scales of 10 to 12 GeV or something like that, then it sets in 7 orders of magnitude. I'm just, translating density, which is in typical.
I agree.
So I look at the typical energy scale where it happens. So that's something like 10 to 11, 10 to 12 GeV. It's not, TeV or whatsoever.
No, I agree. I totally agree. Yes.
Okay, next question.
I actually have 2 questions. So one is very short on your 3 assumptions.
Mm-hmm.
You made an assumption in the equation of state, right?
Yes.
Do you actually need conformal symmetry, or do you
No.
scale invariance enough?
I don't know. I'm not sure.
I would guess that scale invariance. Exactly.
Right. It's no, that's correct. That's correct.
Okay.
It's scale symmetry at leading order. Of course, it's broken at subleading orders. Yeah.
And the other is if I would want to capture that in some numerical simulation of classical dynamics, I would need to add a term that represents the T mu nu of the anomaly, right? Have you considered like what you would have to do?
So I didn't understand the question.
Well, if you just write down the Einstein equations and you would want to see that effect, you're not going to find it because you haven't added the trace, the anomaly, right? So you have to add a suitable term.
No, but you have to add the anomaly.
But so what exactly does that term look like? Can you?
Oh, this one you mean?
Yes.
It's not known in general. So people have been working on this for decades to try to determine the components of this thing. But the problem is that the components are plagued by renormalization scheme ambiguities. So it's very hard to tell what the components are. But in the 60s, in the 70s, what people learned is that what is renormalization scheme independent is the trace of this object. So practically, I would say the only case where in higher dimensions, in 2 dimensions more is known, of course, but in 4 dimensions, the only case that I know where the components of this object are known, so if you wanted to solve the full Einstein equations, is in the case where you have a conformally coupled theory and the background is conformally flat. In that case, you know exactly, there's an explicit formula for this in terms of the Riemann tensor and so on. Yeah.
So last question over here, please.
I think I must be misunderstanding something fundamental. Can you help me understand in your equation for the breaking of the conformal scaling of the
This one.
classical piece of the stress tensor, why it is that it doesn't... Did you turn off the mic? I must be misunderstanding something very simple. Can you help me understand in that equation why it is that this matter equation of state doesn't involve something like the number of particles of the thing, or the what is the parameter rho, for example?
It's the energy density.
Energy density.
Yeah.
Okay, so if I were going to make an estimate of that, for a degenerate electron star, I would,
right.
For a white dwarf
star.
Yeah,
so in that case, let's say P would be the Fermi pressure.
Right.
And rho is, the other component in the stress tensor.
What would alpha be in that case?
Oh, 1/2, yeah. In that particular case, alpha is 1/2, and the m appearing in the equation, this m is the mass of the fermion. If you do quantum statistical mechanics, you take the relativistic limit. This is you can find this in the textbooks. This is textbook stuff. For that case, alpha is equal to 1/2, m is the mass of the fermion, and then if you just do quantum statistical mechanics, you take the ultra-relativistic limit, this is what you get at leading order.
Okay, thank you.
Okay, so we run out of time. Please postpone further questions to the coffee break, and thank you to the speaker, please. So the next speaker will be Yazaman Yazdi, ever-present lambda cosmology.
Thank you. I am going to talk about the ever-present lambda cosmological model, which is related to causal set theory. It's a very old idea dating back to 1987 when it was first introduced by Raphael Sorkin. And for more details on this topic beyond what I'll cover in this talk, I encourage you to have a look at this paper. So there are 2 key properties of causal sets that are the main ingredients of the ever-present lambda idea. One of these properties is related to the dynamics, And one of these properties is related to the kinematics. Let me start by telling you about the property that's related to the dynamics. In classical dynamical models, a causal set grows element by element sequentially. So in this diagram, one step of such a growth process is represented. This 4-element causal set here can grow into one of these five-element causal sets above it. And because of this elemental growth of the causal set, the number of elements in a causal set plays a role similar to time. And this is the key ingredient that we'll need from the dynamics, that the number of elements plays a role similar to time. Now for the key point that's related to the kinematics, causal sets that can be approximated by continuum space-times have a number-volume correspondence such that if we were to take one of these discrete causal sets and embed it in a continuum manifold, there would be this number-volume correspondence such that the number of elements within any arbitrary region with volume V would be statistically proportional to that volume V. And the Poisson distribution ensures this number-volume correspondence with minimal variance. So whenever we want to study causal sets that resemble a certain space-time, we focus on those that follow this Poisson distribution. And if we set that proportionality constant between the number and volume to 1, that means that according to this distribution, statistically, the number of elements in a region with volume V, the mean number would be V, and the standard deviation would be square root V. We also have a converse relation that an n-element causal set can be approximated by a range of volumes given by the Poisson distribution. And this Poisson distribution relation is the key point that we're going to need from the kinematics. So now let's see how we put these two things together and arrive at the ever-present lambda idea. Imagine that we are in a regime where the dynamics can be approximated by an effective continuum, gravitational path integral. For example, with something like the Einstein-Hilbert action in the exponent here. Remember that from the point of view of the causal set, the number of elements plays a role similar to time. So a natural constraint to put on such a gravitational path integral would be to hold the number of elements fixed, analogous to the usual holding of a time interval fixed. And because we're in an effective continuum picture here, that translates to holding the space-time volume fixed. And this is also a version of what is considered in unimodular gravity. Next, let's perform a Fourier transform on this expression where I've labeled the Fourier transform variable lambda, but at this point it's just an arbitrary variable. If we were to reverse the order of integration and apply the volume constraint, we would find that this, our arbitrary lambda Fourier transform variable would appear in the resulting expression in the same way as a cosmological constant would appear. So we can interpret it as a cosmological constant. And because this lambda, our Fourier transform variable, and the space-time volume V are related by this Fourier transform relation, they are quantum mechanically conjugate and have an associated uncertainty relation. So delta lambda over 8 pi g times delta V greater than or equal to h bar over 2. And we can actually learn more about this uncertainty relation using our insight from the causal set kinematics. So even though up here we were looking at an effective continuum picture, we still really want to have an underlying causal set in mind. And remember that an n-element causal set can be approximated by a range of space-time volumes, and the spread in those volumes is described by the Poisson distribution. So we interpret this delta V in the uncertainty relation as the standard deviation of the Poisson distribution. And since we are in this regime of talking about continuum correspondence and continuum approximations, we are in a regime where we're assuming both the number of elements and the corresponding space-time volume are very large. So the Poisson distribution in this regime tends to a Gaussian distribution, and we saturate this uncertainty relation. So this is just the same uncertainty relation where I've dropped the h bar and a pi g constants. So we have this relation delta lambda delta v approximately 1. And given that we have delta v, we also have delta lambda now. We just move this down. But nothing I've said so far helps us determine the mean value of lambda. We just know its standard deviation. And this is a part of the argument that will need further justification in the future. I'm just going to follow what has been done in previous work and assume that the mean about which lambda is distributed is 0. So with that assumption, now let's put everything I've told you together. So lambda goes as, statistically, it goes as its mean plus its standard deviation. We've assumed that its mean is 0, so it just goes as its standard deviation. Delta lambda goes as 1 over delta v. Delta v is given by the Poisson distribution, so it goes as square root of v. And now let's connect this to our universe. So we can substitute the volume of the observable universe here to connect this to our universe, which in 4 space-time dimensions goes as 1 over h to the 4. So it approximately, lambda approximately goes as h squared, where h is the Hubble parameter. And then finally, if we substitute in the value of the Hubble parameter today, we would get 10 to the minus 121 in Planck units, up to a sign. And this is close to the observed value of the cosmological constant, and it is in this way that ever-present lambda suggests an explanation for the value of the cosmological constant today. But notice that by this argument, lambda statistically follows 1 over square root v, not just today, but at all epochs. And that's why it has the name ever-present lambda. So this was the main idea of ever-present lambda, that at all epochs, it statistically goes as 1 over square root v, with a sign that can be positive or negative. But we still need to know a couple more things in order to be able to simulate the evolution of lambda and to know how its values at different times correlate with one another. A concrete model that offers this was given in this reference. And the main idea of this model, which is called Model 1, was to assume that each causal set element contributes to the cosmological constant part of the action an equal amount in magnitude, but with random sign. And there's a free parameter in this model, which I've called alpha, which sets the magnitude of this single element contribution. I'm not going to go through more of the details of this model, but essentially one would then add all these single element contributions to the past light cone of an observer at any epoch, And then at each later time, you would just add the extra elements in the past light cone. So we consider the past light cone so that it's a causal volume that we are considering. And I just have time to show you one example of how this model does when tested against standard observational data. So along with Santanu Das and Arat Nasiri, who is also here, we carried out an analysis using supernova type 1a data. We did an MCMC analysis using 20,000 random number seeds. And we used the chi-square value of lambda CDM as a quantitative reference point for how the model does. What we found from our 20,000 size sample was that 3 of the histories had a chi-square better than lambda CDM. Here are the distributions for the present-day matter density and Hubble parameter for the 27 best cases that we had, and the 3 best ones are marked with dashed lines. So the Hubble parameter values are constrained to be around where we'd expect them to be, but the matter density is not constrained. And another qualitative feature that we noticed in this analysis was that the good ever-present lambda histories tended to have smaller dark energy at lower redshifts compared to the matter density than the bad histories. So in this figure, the colored jagged lines are the ever-present lambda histories for the good samples, and the dashed curves are the corresponding matter density, and the black ones are the bad histories. So you can clearly see this qualitative difference of the colored ones being smaller than the dark ones. So in summary, ever-present lambda is a model for a fluctuating cosmological constant based on causal set theory. The fluctuations are both in magnitude and in sign. And there are many open questions that remain regarding this idea and models that have been built to describe it phenomenologically. And there are many opportunities for further investigations. So thank you.
Thank you very much. Questions to the speaker? Okay.
2 short questions. First, in the comparison with seeds, does each seed correspond to a history?
It corresponds to a string of random numbers, which then creates a history.
So out of 20,000 trials, you got 3 that looked like they might agree with the data better than lambda CDM. Is that correct?
Out of the 20,000 seed, yes, strings of random numbers.
Okay, so second very short question is, why is it if the induced cosmological constant is always comparable to the volume, why is it that we can see back to eras like radiation domination or matter domination, like at the CMB, that seem to be, or like at nucleosynthesis, that seem to not have a cosmological constant at all, that seem to be just radiation dominated or matter dominated?
Well, first of all, so it's statistically going as 1 over square root v. So the mean is still, the fluctuations are about 0. And a lot of the effects that we see are actually integrated effects. So it's important that it can be positive and negative over different eras. And observationally, the observational test attests to it. We can describe such things with such models. And there are other dynamical dark energy models that can do so as well. It's not in principle in any contradiction with there being a radiation-dominated era or matter-dominated, if I understood.
One final question here, please.
Yeah, at some point you mentioned that your model was similar to unimodular gravity. So can you give some precision, because in unimodular gravity it's just the diffeomorphism which preserves the infinitesimal volume which are allowed. In your case, I don't see in which sense it's similar.
So the only similarity was in the spirit of having a fixed volume constraint. Now, the fixed volume, it's a global volume. It's a global volume rather than a local volume, which is more traditional in unimodular gravity. But that's the sense in which there's a similarity. There's a fixed volume constraint on the path integral, and that's as far as the connection goes.
I see. Thank you.
Yeah.
So let's thank the speaker again. And we move on with Eleonora Giovanetti. How to constrain the universe anisotropies across a big bounce.
Can you hear me? Okay. So, thanks to the organizers, and good afternoon to everybody. I'm Eleonora Giovannetti, and today I will talk about the quantum behavior of the anisotropies for a Bianchi-Knight model in a bouncing picture. In particular, this talk is based on this paper, in which we investigate the possibility to avoid the unlimited growth of the anisotropies arbitrarily close to a bouncing point. This is a brief outline of the presentation. I will start with introducing the two main technical instruments that we use in our investigation. Then I will focus on the core of the analysis, that is about the quantum behavior of the anisotropies, and then I will outline some final remarks. So let's start with polymer quantum mechanics, that is an alternative representation of quantum mechanics that we use in our investigation. It is not equivalent to the standard Schrödinger one, but can be introduced by following these simple steps. In particular, one chooses a basis that is orthonormal in the Hilbert space with a parameter mu that is a real parameter. And then one introduces these two main operators, the label operator that acts in this way, and so that it is discrete in the sense that the set of its eigenvalues is related to states that are all orthonormal. And then the shift operator that acts in this way, and that is discontinuous in the sense that after its action, the final state will be always orthonormal to the initial one, no matter how small is this parameter lambda. So the importance of polymer quantum mechanics in cosmology is the fact that it is able to implement some cutoff effects. In particular, it is able to reproduce loop quantum cosmology phenomenology with a simpler mathematical formalism. And the important thing is that if we choose as discrete our configurational variable that in cosmology is often a geometrical quantity related to the scale factor of the volume, the conjugated operator does not exist. And this can be shown, for example, for a one-dimensional mechanical system in the momentum polarization. We can see that the Q operator acts in this way, in this polarization, and corresponds to the label operator, so it's discrete. And that the shift operator has this exponential expression, with the consequence that since it is discontinuous, P does not exist as a well-defined Hermitian operator. So the standard procedure in polymer quantum mechanics is to introduce a polymer lattice in order to regularize the theory. Mu is the fundamental length, that is the polymer parameter. We can, obviously, in order to deal with a well-defined dynamics, we have to introduce a regularized version for this operator that is not well-defined. So we restrict the action of the shift operator on this lattice that is well-defined, and we introduce a modified version for the momentum operator, in this case by means of the same function, so that we can deal with a well-defined Hamiltonian, and we can study the cutoff effects in our cosmological dynamics. The second instrument that we use is the Vilenkin approach that comes from the need to solve the wave function interpretation puzzle in the Wheeler-DeWitt formalism. The starting point is the splitting of the phase space into two regions, the semi-classical one and the quantum one. In particular, the main hypothesis is that the quantum region is small and the effects on the semi-classical region are negligible. In this case, we can recover a time evolution because the quantum fluctuations are negligible. Therefore, since these two regions are orthogonal, we can write the universe wave function in this way. In particular, this is the semi-classical part of the wave function with S that is the semi-classical degree of freedom, and chi that is the quantum part. And in particular, this contribution is VKB expandable in H bar. Then the last hypothesis is that the dependence of chi on S is parametric, so basically it is a Born-Oppenheimer approximation on the universe wave function. Then by using these three hypotheses from the Wheeler-DeWitt equation, we can obtain order by order three different equations. At the zero order in each bar, we obtain the Hamilton-Jacobi equation from which we can derive the phase S of this wave function, that is basically the classical action. Then at the first order in each bar, we obtain the amplitude A and from the continuity equation, and we also obtain the Schrödinger equation from which we can derive the wave function chi, that is the quantum part. And in this way, we have obviously recovered a time evolution for our quantum system by defining a time variable by means of the semi-classical degrees of freedom, and our probability is positive defined and well conserved. So in our work, we put together these two approaches. We take in consideration the Bianchi-Knight model as our cosmological background. In particular, we consider the Bianchi-Knight model is the most generic, homogeneous, and anisotropic model. We expand up to the second order its potential that depends on beta plus and beta minus that are the two anisotropies. Also, in order to introduce the cutoff effects, we consider as discrete the universe area, that is A, and consequently we regularize the associated momentum, that is PA. And then, in order to introduce also the Vilenkin approach, we split our phase space into a classical phase space and a small quantum one. In our analysis, our classical degrees of freedom are the universe area A and the free scalar field phi, whereas our quantum degree of freedom are the two anisotropies. So, in our analysis, we were able to derive the three Vilenkin equations. The important thing is that polymer quantum mechanics is mainly formalized in the momentum representation, so all the Vilenkin approach has been reformulated in the momentum representation in order to make it compatible with the polymer formulation. Here we have the zero order equation, that is the Hamilton-Jacobi equation, from which we can derive the action S. Then at the first order, we have the continuity equation from which we can derive the amplitude A and characterize the semi-classical part of the universe wave function. Also at the first order in each bar, we have the Schrödinger equation that describes the time evolution of the two anisotropies and from which we can derive chi, that is the quantum part of the wave function. So let's start with the dynamics of the semi-classical sector. So why we have introduced the polymer quantum mechanics? Basically, we want to reproduce the bouncing behavior in the background. So this is the semi-classical part of the Hamiltonian with our classical degrees of freedom that are phi, the free scalar field, and A, that is the discrete universe area here. So in order to solve the dynamics, we fix the time gauge. Here we have the Hamilton equations. And then by fixing the initial conditions, we find the evolutions for the universe area and its conjugate momentum. As you can see, the singularity is removed and the universe area experiences a bouncing behavior. So the universe first collapses, then reaches the bouncing point, and then expands without reaching the singularity. So this analysis shows that by considering as discrete the universe area, polymer quantum mechanics is able to reproduce a big bounce. At a quantum level, we have recovered a Schrödinger equation thanks to the Vilenkin approach that governs the behavior of the two anisotropic degrees of freedom. Here you can see that the Schrödinger equation in this case is a time-dependent harmonic oscillator. And the crucial point of the analysis is that thanks to the presence of the potential, that is this term in brackets, that is not the exact Bianchi-Knight potential, but is its expansion up to the second order, we have that the polymer effects that are applied to the semi-classical background, because our discrete variable is the universe area and is our it is our semi-classical degree of freedom, enter also in the quantum dynamics because the time-dependent frequency of our harmonic oscillator is the universe area itself. So by changing the behavior of the universe area in time, we change the eigenstates of the harmonic oscillator. So in this case, we have solved this harmonic oscillator and found the eigenstates, and here you can see the associated probability density, by considering the bouncing behavior for the universe area, as I showed you before. Now we have all the ingredients to compute the mean value and the variance of the anisotropies and to analyze their quantum behavior arbitrarily close to the bouncing point. In particular, we have exactly computed the mean value and the variance by using the action of the creation and annihilation operators on the eigenstates. So obviously the mean value is 0, so if we consider the universe in one of the eigenstates or in a Gaussian superposition of eigenstates, we are basically considering the universe in a quasi-isotropic state. And the variance takes this expression, and as you can see, for different energy levels, the behavior is confined and as an oscillatory character, arbitrarily close to the bouncing point too. So in this case, if we start with a quasi-isotropic state for the universe, we have that the anisotropies are under control during the evolution. Also, we have computed the mean value and the variance also for the shear quantity. That is a quantity that accounts for the anisotropic character of the model, since it is basically related to the gap between the three Hubble parameters. By using the annihilation and creation operator, we exactly computed also the mean value and the variance of Q, that also have this oscillatory and confined character along time. So this analysis supports the fact that if we are dealing with a harmonic potential that depends on the anisotropies, we were able to avoid the growth of the anisotropies arbitrarily close to the bouncing point. And so far, we have demonstrated that the presence of harmonic potential is a necessary condition in order to maintain the universe in a quasi-isotropic state. But is it also a sufficient condition? The answer is negative, in the sense that if we consider a different behavior for the universe area, so not a bouncing solution, but for example a singular collapsing branch, we have that the variance of the anisotropies diverges in time. So our quantum state is completely delocalized, and we cannot infer anything about the constraining of the anisotropies or their evolution in time. In particular, if we start with a quasi-isotropic state for our universe, it is not ensured that arbitrarily close to the singularity, the universe is still quasi-isotropic, but it can be completely anisotropic. So, to briefly summarize, in this work we have reformulated the Vilenkin approach in the momentum representation to make it compatible with the polymer formulation. In particular, the use of the Vilenkin approach is important in order to recover a Schrödinger type time evolution for the quantum degrees of freedom. We have split the phase space into a semi-classical part and a quantum one, and decided to describe as quantum the anisotropic degrees of freedom. We have also implemented polymer quantum mechanics, and we have demonstrated that polymer quantum mechanics is able to reproduce a bounce when the universe area is chosen as discrete. We have analyzed the Schrödinger evolution of the anisotropies on a semi-classical bouncing background, and we have demonstrated that the presence of the quadratic potential for the Bianchi model is able to maintain the universe in a quasi-isotropic state. Also, we have demonstrated that the presence of the potential is necessary, but is not a sufficient condition, in the sense that if the background is singular, the quadratic potential is not sufficient to avoid the unlimited growth of the anisotropy. So the important thing is that thanks to the presence of this potential, we are able to introduce the polymer effects of the background at a quantum level. Thanks for the attention.
Thank you, Eleonora, for the nice talk. Questions, please?
Da exist simple models of a scalar field coupled to gravity, where in the Einstein frame you have a bounce, but then there exist other frames where everything goes completely regular. So in these models you have, of course, full control of the fluctuations. Have you ever checked that your method really works well with this type of methods for this type of particular models? I mean, that would help a lot in order to see, you know, if the approximations really work or not.
Okay, do you mean in other frames? Can you repeat the question? I think I don't.
Well, you know, you are free to choose your metric frame.
Yeah.
So there are models where in the Einstein frame you have a bounce, that's a real singularity, and then you go to a different frame, and there everything just goes smoothly through the bounds from one side to the other. The scalar field just changes sign, and that's it. So of course in these models, since the effective action for this model is known, you can compute the fluctuations, and you can really follow what happens when they go through the bounds, and that should be a good way of testing your approximations and your assumptions, because in this case you have full quantum field theory control of everything.
Yeah, okay. We didn't check, but the fact is that when you reproduce the bounds in polymer quantum mechanics, changing frame and changing the metric variable that you're going to discretize, it's a really subtle issue.
But not on the, you know, not on the effective action. Once you have that, you can of course change variables.
Yeah, but it's not easy to do this when you quantize on a lattice, because the presence of the minimal length makes non-trivial the identification of the canonical transformations. So you're not sure if when you change the variables you are doing it in a canonical way. This is not clear in polymer. That's the point, but it's obviously useful to verify if the results are conserved in other frames, but we didn't check this here. Thank you.
Okay, thank you. So the final speaker of this session. Lucia Menendez-Pidal, The Problem of Time in Quantum Cosmology from Different Perspectives. Thank you.
Okay. Thank you very much. Thank you very much for allowing me to speak in this session. And yes, I will talk about the problem of time from different perspectives, namely the canonical quantization perspective and a little bit of the path integral quantization perspective. So I have given similar talks in the past, but I will try to tell it in a slightly different way. So yes, we're going to work on the problem of time in a cosmological toy model, and my toy model is basically a flat FLRU universe. Instead of working with the scale factor A, I will work with the scale volume, which is proportional to A cubed, just because it was simpler mathematically. And the matter component of my model is a massless scalar field, and a bit the spicy component of my model is a cosmological constant, but this cosmological constant comes from unimodular gravity a la Taterboim. So instead of being a simple plain cosmological constant, it comes with its conjugated coordinate. But for the purpose of this talk, the only thing you need to know is that I have a toy model that has 3 pairs of canonically conjugated variables. One of them is T and lambda. This lambda is my unimodular gravity cosmological constant. One pair is my scalar field phi and its conjugated momenta, and the other pair is my scale volume, which is defined to be positive, and they're all canonically conjugated. We can write the Hamiltonian of our system, and it has this expression where n here is the lapse of the metric, and because this is a totally constrained Hamiltonian, we have to set this constraint equal to 0. And we can see that it's a function of the variable of my model. And this model is a cosmological model that has a big bang and a big crunch singularity. So now we want to quantize this. And we can quantize it in the gauge n tilde equals 1, in which we have this constraint, and we can obtain the Wheeler-DeWitt equation. Well, we will quantize the model using the Wheeler-DeWitt equation, and in this case, if one ordering or one way to obtain a Wheeler-DeWitt equation from this constraint is to go from here to this equation, in which the important part is that I have a DDT term here. So basically, if I take this operator and I put it on the other side, what I find is a Schrödinger equation in T. So this Wheeler-DeWitt equation is suited to use this parameter T as a relational clock to express how the rest of the variables of my model vary. However, we can also choose to quantize this model in a different gauge, namely taking n tilde equals v squared. So instead of having this constraint, we have the same constraint but multiplied by v squared, and we would obtain the same Wheeler-DeWitt equation, but this time multiplied by v squared. And this Wheeler-DeWitt equation is nice because now we have a second derivative with respect to phi. So if I move everything else on the other side, I have sort of a Klein-Gordon equation in phi. So far, these Wheeler-DeWitt equations have the same solutions because one is only v squared times the first one. Therefore, there is some sort of covariance in the quantization. But if we do the further step of the quantization, we will see that things start happening. Namely, let's take the theory that we call the T clock theory, which is where we chose the n tilde equals 1 gauge. If we want to build a Hilbert space of this theory to see how observables evolve, what we find is that dynamics are governed by a Schrödinger equation of this type, in which H is an operator that depends on the rest of the variables of our model. And our Hilbert space is defined by this inner product, which is an integral over V and phi. To ensure unitary dynamics, we need this H, this Hamiltonian, to be self-adjoint. However, the Hamiltonian is not directly self-adjoint, but admits a family of self-adjoint extensions that are parameterized by this boundary condition. The only thing you need to know about the boundary condition that I'm showing here is that it is a reflection around V equals 0. And I should point out that as V is the scale factor cube, V equals 0 is the point in where classically we have the singularity. And so this boundary condition leads to singularity resolution, as we can see in this type of plot. Here I have plotted V as a function of T. The black line is the classical solution, and the dotted lines are quantum expectation values of V as a function of T in this quantum theory for semi-classical state, and the differences between these two curves are only different choices in the free parameters we had. And we can clearly see that instead of reaching V equals 0, the quantum theory, or quantum expectation values, never reach V equals 0 and exhibit some bouncing behaviors. However, we can work in the other theory in which we had a Wheeler-DeWitt equation that we obtained from a different classical gauge, and this time the dynamics are governed by the Klein-Gordon type equation, and we have a Klein-Gordon type inner product, but we have the same issue, that our evolution operator has to be self-adjoint, and it's not self-adjoint initially, rather it admits, once again, a family of self-adjoint extension parameterized by this boundary condition, which looks exactly the same than the one I had before. However, this time, instead of being a reflection around V equals 0, it's a reflection around V equals infinity, which is the spatial volume of my universe. So this boundary condition is going to lead to something that we called spatial infinity resolution, as we can see in this plot. This time, I plotted V as a function of phi and also calculated the same quantum expectation values. And here we can see that the quantum expectation values, instead of going to infinity, they reach a maximum that is finite, so my universe expands and then recollapses. So in the canonical theory of this toy model, we have seen that to ensure unitary evolution, one must impose additional non-trivial boundary conditions, and these different choices of laps that classically do not, or my theory classically is covariant, so the choice of laps doesn't matter, But here, the choice of labs lead to different boundary conditions, and the dynamics, in particular singularity resolution, are affected by these kind of choices. So don't leave just yet, because I have more. So the first thing we thought is that the canonical theory seems to be non-covariant, and we have this unitarity issue. What happens if now I want to analyze the same toy model, but from a different perspective? The path integral quantization formalism is supposedly covariant, so the question we ask ourselves is how to analyze this problem in the path integral formalism, and what happens to unitarity and these boundary conditions. So just a recap of what path integral quantization is very loosely. So it is sort of a probability of going from an initial to a final configuration, and in this type of models, because we are a universe, the final and initial configurations are usually given by the metric, or if you have extra matter, well, the extra matter, no? And this is done by doing a functional integral over the metric and the matter degrees of freedom weighted by the Einstein-Hilbert action, right? So how do we do this in our model? So path integrals in cosmological models have been analyzed, and typically they have this kind of form. So in our model, we have, remember, we have three variables: my volume, my field, and t, which is related to the cosmological constant. So my path integral would be a function of a final configuration and an initial configuration of the functional integrals over the variables, my canonically conjugated variables, the coordinate and the momenta, weighted by the classical actions. I have to add extra terms here that are made to make this integral gauge invariant. In this setting, gauge invariant means incovariant under the change of labs. So I can write my theory in the T-clock theory gauge, namely n tilde equals to 1, in which I would have this action here, in which see that what is under the bracket is the first constraint I have, but I could equally write my action with the other gauge we analyzed, which is basically the gauge in which the constraint has this form, and this action, without specifying, without explicitly calculating these terms, because of this, is covariant or invariant under this change of gauge. And well, when doing this path integral, we could simplify one of the functional integrals, but in particular the integral with respect to v is very hard to find an expression for it, because v is defined only on the half line. So we encountered some problems, namely that finding an analytical expression of this is very hard. So we thought, okay, we have a canonical theory. Typically in quantum mechanical models, people can relate the canonical theory to the path integral quantization, and they do so by these kind of formulas, in which you have your probability or amplitude, and you write it as an integral of this E would be the energy of your system, of the eigenstate of the energy associated with your canonical theory. So here this phi E would be energy eigenstates of my canonical theory. But in our case, we had two different canonical theories, so that correspond to two different choices of labs. So what is going on? So there are a few ways of treating with these models in which you don't have a self-adjoint Hamiltonian, namely not very easy, but the first toy model we looked at is the free particle restricted on the half line, for which the Hamiltonian is not essentially self-adjoint. And what they do here is that to relate the path integral to the canonical theory is that they add boundary terms, they incorporate boundary terms in the path integral, so they add some extra terms. But in this simple model, simple canonical quantum mechanical models, they don't have this lapse issue. So it is always clear which boundary terms they have to add to the path integral. In our case, these boundary terms would depend on the choice of labs that we made in the canonical theory. So in the end, we lose again covariance. So to conclude, this is very much work in progress, so I don't have all of the expressions and stuff, but I just wanted to show you this because I thought it is very interesting. So what have we seen in this talk? How in a simple model, different labs choices affect the result of the canonical quantum theory by introducing extra boundary conditions, and these extra boundary conditions ensure unitarity, but we break covariance. And how this loss of covariance is also manifest in the path integral formalism, because at the end, if we want to take into account unitarity, we need to add these boundary terms that again depend on the labs, so we kind of lose the labs covariance that we had initially. And what we want to do in the future is to have a better understanding of the boundary terms that appear in the path integrals and do further calculations in this model. So, yes, thank you.
Thank you very much, Lucia. Questions?
Thanks for the nice talk. So at the beginning you showed us a plot for the expectation value of V and how it resolves the singularity. How large are the fluctuations of V at this point?
You mean here, right?
Yes.
So they are larger than here. I have some of the calculations in my thesis. For these two specific cases, I don't know, but it's true that they can be quite large.
Yeah, I just
so
mean like,
there is some uncertainty going on.
Right.
there.
So is it okay to like truncate to just the expectation value, or you should look at higher moments? I mean, we need to take into account higher moments as well near the singularity.
Yeah. So you should take this value with a pinch of salt, no, because the uncertainty can be quite high. But you can certainly have cases in which the uncertainty still gives you something strictly above 0. Yes. But they will depend on the, because these are semi-classical states, on the parameters of the semi-classical states.
Okay, thank you. I think it's time to thank all the speakers and the final speaker for their nice presentations. And we will have the ice cream now, and we reconvene at 4 o'clock. Thank you.
encouragement. You also sometimes need to encourage them to fill up in the middle. Is it? It is on, yes, it should work. Okay, so if you're close to the door, please come in so that we can start. And if you can move towards the center so others can also sit. Okay, welcome back everyone. Today's afternoon session, we have two 25 minutes talks, plus 5 minutes for each questions for each talk. So they asked me to stay here because Zoom people should see us. So the first talk is by Shuda Brahma on quantum gravity in de Sitter space. So yeah, take it away.
Thanks. Thanks to the organizers for this invitation, and I'm going to present, so I was asked to talk about quantum gravity in de Sitter space, and I'm obviously going to talk about some of my personal perspectives on it by this rather provocative title. I really don't mean this equals, I just mean that there's a lot to be learned from quantum information techniques, and we have learned a lot about quantum gravity from using them in black hole spacetimes, and perhaps there's a lot to be discovered from using these tools in de Sitter space as well. So most of this work is done with Robert Brandberger, Arjun at Edinburgh, and some PhD students, and also some ongoing work with French group and Lucas Hackle in Australia. Good. So I think I'm not going to justify the use of de Sitter space. I think we all agree that that's something that is useful to describe the very early universe as well as late time evolution. But I still perhaps need to justify a little bit why do we even talk about quantum gravity in de Sitter space, because if we are really interested in describing the evolution of the cosmos as a whole, we are talking about larger scales, why do we even need quantum physics? And of course, a canonical example is that the widespread or the mostly popular paradigm of the early universe is inflation, which not only solves, as we know, the standard cosmological problems, but makes a rather remarkable prediction, which is to say that it explains late time inhomogeneities as we can observe them as temperature and isotropies in the CMB, as originating from quantum vacuum fluctuations. So this is a very rare test bed for testing quantum mechanics. But we can think we can be more ambitious, think bigger. We can think that the quantum origins of spacetime itself has to do something with entanglement. And this is a very popular theme, of course, as I mentioned, in black hole physics over the last decade or so. And is there a description of this in de Sitter space? Can we think of de Sitter as emerging from quantum entanglement of some boundary degrees of freedom? Again, these are just cartoons. I don't get to show a lot of nice pictures, so I'm putting them as much as possible in the first slide. So this first point here, the main message I want you to take away is that observations always access parts of Hilbert spaces. So that just means that whenever we are looking at some part of a Hilbert space, our system density matrix is a reduced one, and that we need to incorporate dissipation and decoherence. There's a very nice talk by Beilok Hu yesterday, and also some very nice talks about this in some of the parallel sessions. So the only so this is very common. This is common to physics, I would say. What is remarkable to cosmology is the nature of the environment. Typically, this is not the kind of environments that we often encounter in condensed matter physics and so on. And I'll describe this a little bit in a little bit more detail later on. In particular, that there's a phenomena called non-Markovianity, where there's a history dependence of the state, where the state came from, that creeps into due to this special environment in cosmology. For the second point about the quantum origins, I'll restrict myself to a very particular thing that I've just become very interested in only very recently, which is complexity as a quantitative measure of the difficulty of constructing this required EPR entangled states, which would be able to explain de Sitter from this holographic degrees of freedom. So I'm going to say a little bit more. I'll explain some of these terms as I go along. So concretely, for the first part, I will consider open quantum systems approach to inflation. That would mean that I would have to consider open EFTs. And that, in particular, I will look at this momentum space entanglement entropy as a quantifier for non-unitarity in the theory, or non-unitary evolution in the theory. For the second part, I will examine this new proposal by Strominger and Cottrell about cosmic version of ER equals EPR, and show that there is a way to actually compute the complexity of this EPR state, and that reveals to us some very nice features of this state, that it is indeed there's some evidence of this cosmic version of ER equals EPR. So if you fall asleep right after this slide, this is the take-home message, which is quantum informatics tools such as entanglement, entropy, and complexity. They seem to be providing us with some very unique and rather unexpected, I would think, insights about quantum gravity. And I could have stopped it there, but because this is something to do with de Sitter space, in particular, I'm a cosmologist. I'm interested in what they have to say for de Sitter space. Also because many of these tools can be verified from explicit string constructions in the case of ADA space. But in de Sitter space, we have to do a bottom-up thing. We don't have string theory to help us. So it's really perhaps in this particular arena that these tools would reveal more to us, even more to us. All right, so the first part, which has to deal with inflation as an open EFT, yeah, again, just for pretty pictures, I'm looking at this cosmic inflation, this very early part of the evolution of the cosmos. So the general idea I think all of us are familiar with is that we thought we would look at higher endpoint functions and non-Gaussianities, and they would tell us about the physics of the very early universe. Only one problem, we have not observed any yet, so perhaps we need a little bit of a fresh perspective. And one such perspective which came out of this is this cosmological bootstrap program, where people take symmetries and principles such as unitarity and locality very seriously and bootstrap all these endpoint functions from these principles. I'll take a complementary view and of this open quantum system applied to cosmology. And in particular, as I already mentioned, observable degrees of freedom in the universe are always necessarily part of a larger system. And modes of, in short, modes of interest, of physical interest, are coupled to an observable stuff, usually. Why is this the case? I'll give you two examples. So in this case, typical UV completions of inflation require some additional fields. So we have like some higher, the field space is not typically one-dimensional if you want some UV completion for inflation. Even though at low energies, it might look like a single degree of freedom. So that these would be examples of UV degrees of freedom to which the inflaton talks to. Whereas also typical models of inflation predict much larger number of E-foldings, like let's say order 500 or 5,000 orders of E-foldings, which means that there's a lot of long wavelength modes in the universe. If this small box is the Hubble patch, is our Hubble patch, and we can only observe these blue fluctuations, there are still these very long wavelength fluctuations which we can never observe directly, and yet they do matter. I mean, our observations do depend where we are with respect to these long wavelength modes, if there is some significant mode coupling. So this is an IR example. These are IR degrees of freedom which our degrees of interest are coupled to. And Wilsonian EFT does not quite directly apply to cosmology. There are many ways of seeing this, from the Feynman-Vernon influence functional, as Belloc was mentioning yesterday, but also like generally because there's no conserved quantity like energy that we can integrate out, and that is not true for cosmology. So what this non-unitarity is nothing to do with quantum gravity. This is a very bottom-up, very an approach that is built on like very well understood physics. We're just looking at some Hilbert space which has some density matrix evolution on it, evolves on this, and we're just tracing out parts of the Hilbert space that we have no access to. So we have some reduced Hilbert space for the system degrees of freedom. The only thing here is that this reduced density matrix can exchange energy and lose information to the environment. So this is what I meant at the very beginning by incorporating dissipation and decoherence. And it is by now it's well known that both of these things are not just conceptual things, they affect observations. Whether they affect it significantly or not is an open question. And this evolution, the evolution equations for this reduced density matrix are commonly referred to as master equations. These are very well studied in quantum optics. For example, these are known as these Lindblad terms. So these are non-Hamiltonian terms which denote this dissipation, which tells you the system can just dump or borrow energy from the environment. However, and this was also like, people have studied this. I'm not coming up with all of this right now. For instance, Arjun, my colleague at Edinburgh, studied warm inflation, which assumes that there's some thermal environment. And many other cold inflation, typical models of inflation just ignore dissipation altogether. The main punchline of this part is that the environment is neither stationary nor thermal, which means that it's somewhere in between, and the Lindblad theorem doesn't quite apply. So the master equation is this Nakajima-Zwanzig type. That's essentially because of it having an out of equilibrium environment. So we need some non-Markovian master equation which needs to be solved for these system degrees of freedom. Again, I have not mentioned everyone who has worked on this for some time now, but Cliff Burgess and Sarah Chandera and my collaborators in Paris, they have been working on it for quite some time now. These master equations are helpful for many things, including resumming late-time secular growth. So in gravity is a system, if you couple something to gravity, there's no way to turn it off. So unlike in collider experiments, where you can have collisions for a finite amount of time. You have free particles at the beginning, free particles at the end. In gravity, if you couple things, even if they're free at the beginning, there's no way to turn off gravity, which just means that the perturbation theory naively fails because of this kind of secular growths in cosmology. One way to deal with them is this dynamical renormalization group method. There's many other, and one way is also this evolution master equation. There's a way to resum them and go beyond the standard perturbation theory. That is what I mean by SPT here, and resum results. This is not something I'll talk about, but this has a lot of this part has a lot of consequence for infrared for infrared modes in cosmology and back reaction in cosmology. Of course, because I'm giving a talk on de Sitter, so I'm only restricting myself to quasi-de Sitter or inflation in this first part. But these techniques are not, of course, exclusive to that. If you have any other model of the early universe that is your favorite, say pyrosis, which also deals with quantum fluctuations, you can still apply open QFT techniques and get some nice consequences, like we put some bounds on the energy of the bounds and so on. Right, so what am I talking about in a little bit more detail? I want, in particular, I just take single field slow roll inflation. I want the short wavelength modes of this to be my environment, and the long wavelength modes to be my system. So modes which are super Hubble, as the modes which exit the horizon, those are the things that we observe later on. And the short wavelength modes are these high energy degrees of freedom, which I will integrate out, or trace out is the right way to do it in this case. I consider a coupling that arises simply because GR is nonlinear. So there's no way to avoid non-Gaussianities. They can be so small that we cannot detect them, but there's definitely nonlinear terms. I take one such term from the cubic nonlinearity. And if you have some other model which is your favorite or which you think is more natural, such as DBI inflation and so on, anything that we derive for this model is sort of a lower bound. You put any more interactions, that will give you more entanglement or more decoherence and things like this. So this is my picture. The red band is my system. The blue band is my environment. There's some quantum gravity theory that I'm not going to be bothered about. I'll just take for granted that this quantum gravity theory can deal with the Transplanckian modes, and I'm not going to worry about that at all. All right, so the goal for us is, can we construct some bottom-up open EFTs? We know how to do EFT of inflationary fluctuations. Can we do open EFT of inflationary fluctuations, which will also take into account these effects of decoherence and dissipation? I'm not claiming that I have solved this, but this is what we aim towards. And then we want to obviously estimate effects of such non-unitary evolution on observations. Do these really have any effect on observations, or are these just conceptual things? Good. So as I already mentioned, I'm going to consider momentum space entanglement in this part of the talk, because I'm going to consider bands of momenta as the subalgebras in which to define the subsystem, and I'm going to trace out over this high energy or this high momentum modes. So what I'm calculating here is perturbative momentum space entanglement entropy to leading order in perturbation theory, and this is a quantifier of this non-unitary evolution for me. And I'll follow the notations in this paper. This is the case for scalar QFT in Minkowski space, because that's what I want to start out with. That's the canonical example. And you get a result that looks like this. So this is leading order in lambda. Lambda is a dimensionless coupling parameter. So you need some interaction Hamiltonian. If you just have quadratic Hamiltonians in momentum space, the entanglement entropy is 0. And this is the leading order term. And this is easily calculable because this is written in terms of matrix elements, which you can calculate in perturbation theory. Good. So what about if I want to try and do this calculation for quasi-de Sitter? We tried this with Robert and a master student a couple of years ago now. And what we find is that there has to be some generalizations. First of all, there's a lot of squeezing going on. So that's this time-dependent de Sitter background which creates particles. That's the squeezing effect. The Hubble horizon is a natural scale to demarcate between long and short modes. That was already in my diagram that I showed you. And again, the cubic interaction doesn't have to be something by hand. That's something given to you by gravity. But of course, the interaction that I showed you earlier implies that we need now time-dependent perturbation theory to calculate these matrix elements. And that's what we need to do. So you find that you need to do some integrals which are rather complicated, and you cannot do them analytically, or at least that's what we thought back then. So we had to estimate them, and we found that this integrand is dominant in this what cosmologists would call the squeezed configuration. So you have 2 environment degrees of freedom and 1 system degree of freedom. So 1 long wavelength mode and 2 short wavelength modes. And this is the result, which is that the entanglement entropy per unit physical volume is something that scales as the slow roll parameter, the Hubble parameter, and the mass Planck. So after doing this calculation, if I was clever enough, we figured out that, and if we could figure out that the squeeze configuration would matter more, which we could actually from some arguments, this you can get from power counting, everything in blue. So that's not a surprise at all. What is rather surprising is this very fast growth of this entanglement entropy. Again, remember this momentum space entanglement entropy. And this was verified later on with my students for just having a spectator field with a cubic coupling in de Sitter. So why do we always find such a large growth in this perturbative entanglement entropy, and how fast is this growth? To compare, to get a measure for how large this is, you can compare this with some background quantities. Let's say the coarse-grained reheating entropy, this thermal entropy, or some Gibbons-Hawking entropy. And you find that this quantity, which is a perturbative quantity, that's evident from this epsilon and so on. This grows very fast, and actually around the scrambling time of de Sitter, it becomes almost equal to this reheating entropy, this thermal entropy. Now that, to me, sounds like there's a breakdown of perturbation theory. That's not entirely surprising. Starobinsky told us about this many, many years ago. What is a little bit surprising to me, however, is the time scale. I would have imagined that this breaks down around like the de Sitter entropy, which is not the logarithm in here. The logarithm makes it very, very fast when these perturbative methods seem to breaking down. So what do we make of this? So if you ask Robert, he would say like that's perfect. That's the Transplanckian time, or WAFA, and they would love it because that's some evidence for the swampland. I'm not that ambitious. I'm just claiming that this perturbative expansion is not trustworthy after this time. But then there's a puzzle. We know that loop corrections do remain under control. There's a lot of people, including people in this audience, who have done these loop calculations, and we know that they remain under control. So the EFT of inflation clearly applies. Is there a way that maybe the open EFT of fluctuations do not? So by that I mean, is there some dissipative effects and so on, which we've ignored? That is the reason for this breakdown of perturbation theory.
So we tried checking this. So we calculated the one loop correction to the graviton propagator during inflation due to graviton 3-point functions. And you find a result which is exactly what you would expect from, or what you expect from standard loop corrections. But we started out with a Markovian master equation. So that's an assumption on our part. We started out with a master equation that is Markovian. And then we find a result for this loop correction, which is exactly what you would expect from standard methods. The standard in method is what I mean. And what is nice is that this exactly matches, but then we can go back and check whether this Markovian approximation was a good one. So we can check what is known as the dissipation of this memory kernel for the environment degrees of freedom. And for a Markovian behavior, you need this memory kernel to go as, which has to be delta function peaked in time. It has to be time local. However, when we check this, we find that this is quite sharply peaked. So it goes as some power of 1 over tau minus tau prime. But it's not delta function peaked. So there are deviations from Markovianity, from strict Markovianity. Now, why did we not use this dissipation kernel to do this in the first place? Why just go back and check that it's non-Markovian? Well, because it's very difficult. So we have to systematically estimate effects of non-Markovianity. But there's a chance that would give rise to some novel phenomena. This is already found by my French colleagues, who found that there's some novel phenomena such as recoherence, which you find if you consider the non-Markovian master equation. At a linear order, you can exactly do this. You can exactly solve this equation. You find there's some really novel phenomena which is specific to curved background like de Sitter, as well as using these non-Markovian master equations. And we are trying to check whether this stays there or whether this persists beyond the linear order. So linear order is obviously a toy model. We want to go to non-linear order to check that. So Markovian environments are pretty difficult to get in cosmology for many symmetry reasons and so on. So we have to check the effect of non-Markovian effects, and maybe that does affect the decoupling of UV modes. That would have some resonance with the Transplanckian problem of inflationary cosmology. Maybe that's where it comes in, and this decoupling doesn't happen as smoothly as one would expect from Wilsonian EFTs. All right, so how am I doing with time? Pretty well, okay, good. So now I come to the second part, which is a bit more ambitious, and which talks about the emergence of de Sitter space itself in some entangled state. So this is something very new to me. I'm not an expert, and I realize that all the holography talks are tomorrow. So I'm just going to flash you a slide to tell you about, like, just the slogan, which is this ER equals EPR, that just says that, you can construct the full bulk black hole state from entanglement between boundary degrees of freedom. And this is like the cartoon for this, I guess, which is showing that if this entire wormhole solution comes from entanglement between these boundary degrees of freedom, and if you don't have this entanglement, then there's no wormholes. All right, so this state is rather special in this context. This is the state of time t equals 0, this thermophile double state that defines these bulk states in this double-sided ADS black holes. So what I want to focus on in particular, so I'm guessing you'll hear more about this tomorrow at the plenary sessions. So what I want to focus on is this very limited point that we already know for, again, 10 years now, that although entanglement entropy and this RT formula for entanglement entropy is the main evidence we have for this slogan, we also need to go beyond entanglement. And that's just because quantum states continue to evolve after thermalization, and Susskind proposed that maybe complexity is the right measure to quantify this. So the way I'm going to think of complexity is in this terms of this computational complexity or circuit complexity. And I'm going to say that this is what quantifies the difficulty, which is like a hand-wavy way of a high-energy physicist way of saying what this is, to construct an entangled state from another rather simple factor state that we start out with. And in particular, I'm going to look at de Sitter space. Of course, that's the interesting bit for me. So I look at de Sitter space, but in this rather weird hyperbolic slicing, and this is also quite well known now. And if I define a wave function in the space like hypersurface everywhere, I define a wave function of the bulk. So I have to define my Euclidean vacuum or Bunch-Davies vacuum everywhere on this dark shaded line. And this L and R regions, just remember this, is bifurcated into two left and right regions. So what's interesting is that I will start with a state, that is this factor state, the vacuum in the L and R regions, and neither this L vacuum or this R vacuum are states in the de Sitter-Hilbert space, because they don't have de Sitter symmetries. But then we can write down the Bunch-Davies as an entangled state over this L and R vacuum. What is nice is that So this expression is not important. This is this Mij appearing here. But what is nice is that all these L, R, and Bunch-Davies states, these are all Gaussian states. That's why I'm able to apply complexity as this minimum geodesic on space of unitarities, this idea by Nielsen, with choosing some appropriate cost function, which was used by Myers et al. For this black hole case. So if I use that, I can actually compute the complexity. That is a very difficult thing to do if you have some non-Gaussian state here. When you do this computation using this covariance matrix approach, which I won't go into, you find that you get a result that is actually finite. You can't do this integral analytically, but you find that this integral is convergent. You can do this numerically. This is a finite thing. This integral is finite. And this is also proportional to a volume, which is like one of these holographic conjectures for complexity. We are not using that holographic conjecture. We are computing something in field theory, in quantum field theory, a complexity, and we are finding that it bears out the holographic expectation. So why is this surprising? So what we find is the complexity of this de Sitter vacuum is finite both in UV and IR. The UV part is not that surprising because we are considering entanglement between, this is long-range interactions between parts of space-time which are disconnected from each other. Contrast this with the complexity of the Minkowski vacuum of this thermofield double when you compute it from this ultra-local vacuum. When you put QFT on a lattice and you compute this complexity, that's a divergent quantity. However, this one is finite, which means that although this L and R vacua don't live in the Hilbert space of de Sitter, this Bunch-Davies vacuum, which is of course a bulk state, it lives in this HL tensor HR Hilbert space, and I can construct it with finite complexity. This is not I don't need infinite complexity. There's no divergence with respect to some cutoff. As I already mentioned, this bears out expectations from holographic conjectures. And this was already shown by Reynolds and Ross that just by the symmetries of de Sitter, if you believe in the symmetries of de Sitter and you apply the holographic conjecture, you expect the complexity to go as 1 over eta cubed. That's what we find. That goes of the volume of this hyperboloids. But we do this as an explicit field theory computation. Again, this free scalar restriction is important because, as I said, if you go to non-Gaussian states, we don't know how to compute complexity. And for our choice of reference state, the complexity seems to be a universal quantity. So this is not something that I emphasized here, but if you look at this transformation, this depends on the momentum as well as this nu, which depends on the mass of the scalar field. But in the complexity, the nu just falls out. I don't know why that happens, but it seems that it's a universal quantity and it's independent of the parameters in Lagrangian. The only parameter is the mass. It depends on the geometry of spacetime. It depends on the Hubble parameter, but it doesn't depend on the parameters of the scalar field Lagrangian. So this proposal so I'll go very fast on this because I'm told I have one more minute. I can tell you more about this in the discussion session if this is not clear. So Strominger and Kotler proposed that there is a version of ER equals EPR, which we can do if you believe in this DSCFT as the dual CFT living on Scri+. So the caveat is that this result obviously has nothing to say about static patch holography or other forms of holography that people use sometimes in de Sitter space. But if we identify these L and R states with this boundary CFT, with the vacuum of the boundary CFT, like Strominger does, he uses a different basis. He uses this quasi-normal mode basis, whereas I'm using this hyperbolic de Sitter slicings. And there's a way, by the way, to go from flat slicing to hyperbolic, as shown by Maldacena. So if I identify this L and R with the vacuum of these boundary CFTs, then the bulk state, or this Euclidean vacuum, can be shown to be a thermofield double state between these boundary CFTs. And this you can show. Of course, I can't show this because I don't have time. And of course, this was already shown that from this state, if you trace out over the R region, for instance, you exactly get a thermal density matrix for the L region as you expect. And this was already shown by Maldacena, but not that you have a thermofield double state if you identify these things with things in the boundary of this de Sitter space. So this is the main statement, that the Hilbert space of de Sitter space is the tensor product of the Hilbert space of this CFT. So I have, unlike in the ADS CFT, where you have one CFT on the boundary of ADS space for de Sitter, and this proposal is of course not due to me, but Strominger, that you need two CFTs on the boundary, and the entanglement between them produces all the bulk states. So I think this hyperbolic slicing is just cleaner, and each of the CFTs just correspond to two of the hemispheres of the S3 on the Scri+. So that makes this a slightly cleaner picture than the quasi-normal mode basis, which I have a little bit difficulty understanding. So I'll just leave my conclusions over here because I'm running out of time. Just mentioning that also this kind of complexity and entanglement plays a crucial role in emergence of spacetime in other models, like such as matrix models of string theory, and I work a lot on those with Robert and Samuel. And there's a lot of things to be checked. We checked already that you can use the same methods to think of Minkowski vacuum as a entangled state over the Rindler vacua. And this was already mentioned by Jürgen Strominger that this should work, and we've checked that this does work. And this seems to be a very generic feature that whenever you have some killing horizon separating two regions and the entanglement between them produces some bulk state, the complexity is finite, and it's independent of the parameters in the Lagrangian. It depends only on the geometry of spacetime. All right, sorry, let's stop here.
Okay, thank you very much for the nice talk. So we start the questions. We have 5 minutes. Please wait until I bring you the microphone. Let's get my exercise today.
I'd like to ask you about the comment of the tensor loop calculation of the graviton propagator.
Right.
And you mentioned that it agreed exactly with some other results, one of which I was in. And I don't understand that statement.
Yeah.
So the 2020 paper was with Nick Tsamis and Lin Tan and myself. And also, parenthetically, I don't think anybody else actually did the full-blown quantum gravitational calculation of the graviton two-point function. Are you sure you have those other references right?
Yeah, you're right. I think all of those references, to the best of my knowledge, like I couldn't find a reference which does graviton loop corrections from gravitons itself. So when we started all this work,
I did. The 2020 did.
Yes,
I don't think those other ones did.
What I'm trying to say is that those sometimes people use like conformally coupled scalars and other things, but it is general.
So it wasn't tensor loops like you said.
It was. So that's what I'm saying. So it matches in the sense that we expect the general corrections to be of this form of this soft.
But that wasn't. I'm not sure what delta sub t squared represents. But if you're talking about the graviton self-energy or the graviton mode function, we didn't get anything that looked like that at all. We got corrections that went like g h squared rather than g squared h to the 4, and we got terms that showed secular growth like logarithm of a. How do you reconcile this? You're using the language in some way I don't understand.
So the secular growth story is something that I tried to avoid, so I didn't mention it here, but I think I have a backup slide on this. So we try to see that there's some secular growth, and if we can just resum that, and that's what we find, that we can calculate it to one loop.
The one loop calculation shows it. Whether or not you can resum it, and I don't, by the way, accept those other authors' statement about resumming it, but whether or not you can resum it or not is independent of the statement of what you actually get when you do the calculation. When you do the calculation, I swear to you, you get a logarithm of a.
I agree. So I think there are two answers to that. One is that I was avoiding questions of the secular growth, so that's not something that I was focusing on. I was just focusing on how it depends on the renormalization scale. But the other question, to answer your question, like you can also redefine your power spectrum, as you probably know, using the 4-point function, and so you use a term from 3-point and the 4-point function, and you redefine your power spectrum, and then this goes away.
That's Senatori and Zaldaryaga stuff, and if you check the literature, you note that I made I thought a pretty devastating criticism of that, and that is that if your point is just that you can turn off any loop correction, guaranteed you can do it. You can define a field redefinition. I can give it to you explicitly, which will eliminate any correction at all to the power spectrum. The question is it the thing that we observe? They did not make a compelling case of that. Nobody has made a compelling case of it. It's an open issue, one that I wish we would talk about realistically as scientists, and one which dogmatic views on that subject are inhibiting an informed discussion.
So I'm just making a comment that if I ignore the secular growth, this is how it scales at the renormalization. I don't understand your comment about the power counting. I thought that was obvious if I use a graviton 3-point function, but we can maybe discuss this in the discussion session.
Yeah, let's keep that for the discussion session. We have time for one quick question there? Okay. This one. Did you turn it off?
Yeah, thanks very much for the very nice overview talk. So I just have a quick question on the complexity calculation, where you say that you get finite complexity. So I guess complexity is not only defined with respect to reference state, but also with respect to choice of operations you're allowed to do, which somehow is probably encoded in the space of unitaries that you integrate over. But then you were referring to somehow long-range interactions. Are you allowing for something like long-range operations in your definition of complexity?
Yeah. So in this particular, you're right, absolutely. But in this particular case, it's much restricted because these are just Gaussian unitaries, right? So somehow the norm on this space of Gaussian unitaries, which is some SL2R algebra, that, well, it's not unique because you have to choose a cost function, but that defines the complexity. Now the long-range interaction story is just saying that because this Bunch-Davies is an entangled state of this L and R vacua, which appear here. So that's just the same way that Maldacena computed the entanglement entropy for exactly this picture, and I'm just computing the complexity between this L and R vacua. So that's long range because that's exactly why it's not divergent as the UV cutoff, because I'm not computing the Minkowski vacuum part of this computation. I'm computing something that is symmetric under the transformation of the L regions. So this is a 3-1, I guess. So that's, in that sense, it's long range because these are separated by, these are causally disconnected parts. So that's the long range interactions.
Okay, I see. Thanks.
Okay, thank you very much. Let's thank the speaker again. So our next speaker is Thomas Hertog. He will talk about quantum gravity in de Sitter space. Again, the same title, but from different viewpoint. So, yeah, the floor is yours.
Thanks. Good. Yes, same title, different subject. So I'd like to report on two recent results on quantum gravity in de Sitter space that have to do with the quantum behavior of the background. So whereas in the previous talk we heard a lot about the behavior of the fluctuations, I'm going to be focusing on the quantum behavior of the background. These are the two papers. The first one is a recent paper that I wrote with Oliver Janssen at ICTP and Joel Carlson, a PhD student in Leuven. And in fact, we dedicated this paper to the memory of Jim Hartle, not only because Jim was a good friend, but also because the paper is very much a continuation of the subject that he pioneered together with Hawking in the 80s. As you might know, Stephen and Jim wrote this famous paper, which essentially launched the whole subject of quantum cosmology in a way we understand it today. So the grand idea that came out of that paper in the 80s is, the idea that besides the theory of dynamics, the universe as a quantum system probably also has a quantum state. And we should remember Jim, I think, as really the father of that field, quantum cosmology, that came out of it. And so what they advocated for years and years really was the idea that, okay, that quantum state is as much a part of a final theory as the theory of dynamics. So what is the quantum state and what can it do for us? Well, as you know, they had a proposal in the paper which became known, or which they refer to as the no-boundary proposal, the no-boundary quantum state for the universe. And they were inspired really by simply the idea of the ground state of the harmonic oscillator, which you can express in Euclidean terms. So they wrote down this equation for sort of a Euclidean path integral formulation for the quantum state of the universe, without being able, of course, to tell us precisely what exactly are the degrees of freedom, what does this path integral mean. But as a saddle point approximation, What comes out of their thinking is really the idea that we should be looking not just at the usual expanding spacetimes, but that we should be looking at complex saddle points as the quantum mechanical backgrounds for cosmology. And that's sort of sketched here. The crux of their proposal was that an expanding de Sitter-like universe at late times, up there in the picture, emerges from a complex or a Euclidean no-boundary saddle point. So down at the bottom, space-time behaves more or less Euclidean. The crux of their no-boundary proposal is that there's no boundary, of course, at the bottom. Down at the top, the space-time behaves Lorentzian. And that simple idea, so turning time essentially into a space dimension, that simple idea comes with a number of key predictions. The one prediction on the left there is that our usual FLRW expansion, classical cosmological evolution, is an emergent property in that quantum theory, and it emerges in a specific way, and it emerges through a phase of a de Sitter-like phase, a phase of inflation. You can only get, when you require there to be regularity, when you require there to be no boundary in the past, a regular compact Euclidean spacetime, well, that essentially implies for you an early phase of inflation. So it's a sense, it's theory of the origin, a quantum theory of the origin of inflation. Next on the right, the condition that space-time behaves regularly all the way at the bottom in the quantum regime where the geometry is Euclidean also implies that the fluctuations are small down at the bottom. If the fluctuations are small initially, it essentially implies more or less a Bunch-Davies vacuum state and therefore an arrow of time when you move up. However, as you know, there are many different models of inflation, and some people say this is a success, others say, well, the theory doesn't quite agree with observations, it can be scattered all around. So you can read this famous Planck diagram in two different ways. And so for a long time, Stephen, Jim, and I looked at this and wondered whether the no-boundary theory of the quantum state could refine the predictions of inflationary theory. So can the no-boundary proposal be a prior that essentially would zoom in on one or another part of this picture and therefore strengthen or refine the predictions of inflation? That's ultimately what you would want from a quantum theory. But it's complicated. It's complicated for various reasons. The first and obvious reason is that any prediction that you might want to derive from a wave function of the universe involves a conditional probability. Just like an electron in quantum theory doesn't have a position before you ask it, well, the universe doesn't quite have a definite history before you ask your question. But the questions we're asking in cosmology are very detailed and complicated and involve a lot more than just thinking about the wave function. The second problem is equally obvious. As I already alluded to, we don't have very much control over the path integral. We have a saddle point approximation. We have no clue about the underlying microscopic degrees of freedom. So what exactly is that path integral, that wave function? And as long as we don't quite know that, the predictions are bound to remain a little vague. And so the two papers that I briefly want to report on are two recent results that go in the direction of refining that theory. So the first one is the one that I already mentioned. What do we do here? Well, Kontsevich and Segal a year or two ago came up with a criterion that would further restrict the use of geometric saddles, complex saddles in field theory. Really, there was their motivation, but then Witten later extended their criterion or sort of elevated their criterion to a selection principle of saddle geometries in gravitational path integrals. And the idea behind the criterion is very simple. you would want your complex saddle point background to be a reasonable background on which you would want to define a field theory. And that because the Euclidean action of the different fields involved is should be well defined. That restricts these saddle point geometries. And there's some evidence for this criterion. If you apply it and if you work it out for known saddle points, well, it eliminates certain pathological wormholes, and it does allow for other complex saddle points which we really want to be, which we really think of are meaningful in a quantum theory, such as, for instance, the complexified Kerr solution, which perfectly fine explains its thermodynamic properties. So we decided, well, decided to ask the question, do the no-boundary saddles satisfy this new criterion? The no-boundary saddles in all these models of inflation that I discussed. So you might wonder, well, what can go wrong with these no-boundary saddles? They are certainly not the most exotic saddle points that we've heard about today or that have been considered. They're fairly straightforward saddle points in which you start with an approximate Euclidean de Sitter space, so in other words, an approximately four-sphere kind of solution that goes through a complex transition phase into a Lorentzian expanding universe. It's not very exotic. But it so happens that a strictly Lorentzian expanding universe is already just on the edge of violating that criterion that Kontsevich and Segal propose. And so it turns out that the way you approach Lorentzian classical cosmological behavior is in fact very relevant to this criterion. And so strangely enough, this criterion tells us something about the quantum corrections to Lorentzian behavior of the cosmological background. So it's a little bit mysterious to me why it does so, because these quantum corrections are buried in exponentially small deviations from just classical cosmological evolution, but it does. On the other hand, down at the bottom there of the figure, things seem fine because the geometry is essentially Euclidean and the criterion is bound to be okay. So we ran all these models that Planck considered, that the Planck collaboration considered. We ran the criterion of Kontsevich and Segal through this. We checked all those saddle points in all these different models, and we found, somewhat to our surprise, that the criterion selects those no-boundary saddles, those models of inflation, if you wish, in which the universe emerges on a concave patch of the scalar slow roll potential. If you translate that statement into a statement about observations, this is what you get. The red lines, so these are 9 or 8 different models of inflation, and I'm varying a parameter, so which in the potential, and the bands are between 50 and 60 e-folds. The red lines up there are excluded regions. So in other words, if you refine the no-boundary proposal with this additional criterion that your complex saddles should admit a meaningful quantum field theory, then you restrict the models of inflation that you can have in the no-boundary theory to those green bands. In other words, you predict that the tensor to scalar ratio of fluctuations should be less than 0.08, roughly. So that's the first result. Yeah, I can pause here if there's a quick question before I move on to the... Yes? Yeah, so these are 8 single field models with 1 free parameter that you're varying, yes. He was asking whether I was assuming single field inflation, and the answer is yes. I'm running these models essentially through my quantum cosmology machinery. Okay. Yeah, so the second part of my talk is connected, yet somewhat different. The second part is, again, this question, okay, can we make some headway on what are the microscopic degrees of freedom behind that path integral? Can we reformulate, can we rethink the gravitational path integral? Of course, the game in town there is to look for a holographic description. And in a sense, this picture sort of reveals already where I'm heading. And the goal of this second part will be just to explain this picture. That's a paper which came out last year with these 4 co-authors. Okay, so let's again have a closer look at these no-boundary saddle points. And let's consider the simplest saddle point. Let's consider exact empty de Sitter space. In that case, the saddle point is a clean half force sphere matched on a sharp boundary onto an expanding branch of the Sitter space. And so it's a sharp Euclidean Lorentzian transition, whereas this was a blurred transition in models of inflation. You can think of that saddle point. Well, its amplitude is given there. The wave function acquires a real part from integrating the action over the Euclidean part of the geometry, and you acquire a huge phase from integrating the action over the Lorentzian expanding part. So the wave function takes a WKB form in which our de Sitter space arises with a certain amplitude. Now you can think of those saddle points as complex solutions to the Einstein equations in the complex time plane. And if you think about it that way, what we have there on the left is nothing else but an integration from the south pole at minus pi L over 2 to the equator of the force sphere, and then up into a Lorentzian time direction to some final boundary. Very simple configuration. The metric is written on the top there. Now, let's look at an even more abstract and yet more fundamental quantity. Let's look at psi star psi in this way. Well, psi star psi, then the imaginary part essentially goes away, and you're left with just a Euclidean part of the amplitude. You're just left with just the amplitude. In the complex time plane, this would be like not going vertically, but essentially it would be equivalent by integrating over the entire sphere. In the set, we have just a sphere. Psi star psi is a quantity which we may not consider physical at all, in fact, some sort of normalization maybe, but in fact, it is capturing there in Euclidean terms, in purely Euclidean terms, it's capturing the de Sitter entropy, minus the action of Euclidean de Sitter space, minus the Euclidean action of the force sphere, is nothing else but the de Sitter entropy. So there's a connection between Lorentzian de Sitter space and the force sphere there. Now, I want to do the following. I want to calculate the exact same quantity, the de Sitter entropy, but going around a different way, going around from the south pole to the north pole of the sphere by going first up, then across, and then down. And the reason and of course I'm going to get the same result. But the reason I want to calculate it that way is that by going up and then down along these vertical blue lines, I discover that the very same saddle point has a different geometric representation in which it looks like a Euclidean anti-de Sitter space with an overall minus signature. And if I calculate the de Sitter entropy that way, I discover something interesting. If I go along the vertical line, the blue line, all the way up, you of course get the Euclidean anti-de Sitter action. That it means I get the deregularized Euclidean anti-de Sitter action and a bunch of counter terms. However, if I then go horizontally, what happens is that I get that the counter terms that I was getting in the vertical part are cancelled and replaced by a phase also multiplying the counter terms. And then the second part of this action is just a complex conjugate. So at the end of the day, if I go around here, then my Euclidean de Sitter action is in fact written as -2, because I get 2 legs here, times the regularized Euclidean ADS action. So there's a natural connection at the level of the wave function of the universe, at the level of thinking about complex saddle points between de Sitter and anti-de Sitter. Whereas if we think classically about cosmology, you would have to come up with some sort of wacky continuation. If you think quantum mechanically about cosmology, then it all amounts to nothing else but a statement that complex saddle points, given complex saddle points of a path integral, have different geometric representations depending on which contour you choose. And so that's this picture. What we want to convey here in the picture in our paper is really, here we have the force sphere, but somehow, and the force sphere captures the entropy of Lorentzian de Sitter space, but somehow that entropy we can also think of as twice the regularized action of Euclidean ADS spaces emerging from these poles and then suitably identified. So in fact, yeah, this picture here, you would be following a kind of that contour. Why am I interested in doing this? Obviously, because once I have an ADS connection, I can use ADS CFT to replace the saddle point by a field theory on the boundary. And so we can add one more ingredient here to our chain of equalities. We started out thinking about the de Sitter entropy, relating it to the action of the force sphere, relating it to the regularized action of an auxiliary ADS space, but that regularized action of the auxiliary ADS space is in fact nothing but a logarithm of the partition function of a dual CFT on the S3 boundary. Where is the S3 boundary? The S3 boundary could be the boundary of these ADS spaces. Or if you wish, you could think of the dual field theory as living on these points. So now we arrive at the conjecture. We arrive suddenly at the conjecture that the de Sitter entropy should be given by -2 the logarithm of the partition function of a dual field theory defined on the tree sphere. So let's check it, because you should be very skeptical at this point. All I've done is I've played around with different geometric representations of a saddle point. So it looks like what I've done is very, very semi-classical. And this is what we thought. And of course, everyone knew already that the leading term, the semi-classical term, the pi over lambda term, matches between these two. So we must now specify, right? If we're going to check this conjecture, we must specify, we must embed our theory in a full 11D supergravity theory. We must identify an ADS CFT pair, which I've done here by considering the ABGM dual theory, and so forth. Then you can calculate, then you can check it, because the partition function of the ABGM theory is known, and so I can calculate it. In fact, it's known, not just the leading order is known, but the whole series is known. This is the term which through ADS CFT matches the Gibbons-Hawking entropy of the Sitter space. But there are all these corrections. And so a key question is, can we reproduce these corrections which take us beyond the saddle point approximation of the path integral? And so that's the calculation we performed in our paper. I refer you to our paper for the details, but it amounts to adding higher derivative terms to your bulk action and computing one-loop determinants around the saddle points that enter, so the S4 cross S7 saddle point now, using techniques developed by Sen and Barmanio 10 years ago. And the bottom line is that, in fact, both this correction and the logarithmic correction match exactly between boundary field theory and bulk. And that is a kind of striking result, because it means that for the first time we have a concrete proposal for the quantum corrections to the de Sitter entropy, and a vague idea of this perennial question: what does the de Sitter entropy actually count? A question which was open since 1977, and I think we have an answer. The microscopic de Sitter entropy does not quite count microstates. It's associated with the partition function of a holographically dual CFT defined on a tree-sphere. There's no time and there's no Hamiltonian, and so it's probably a little too naive to talk about microstates. Also, the exponential of the quantity that we get out of that holographic field theory is not an integer, and so it would not really be, you couldn't say it's a number of microstates. But on the other hand, being given by a QFT path integral, the entropy does clearly represent some sort of measure of degrees of freedom, and likely some sort of entanglement of those degrees of freedom once we interpret it in the Lorentzian. What remains to be done? What remains to be done now is to extend that kind of holographic thinking about the no boundary wave function to include sources, to include observables, to include, to calculate more tangible quantities that are relevant in cosmology compared to that abstract de Sitter entropy. So that's it. Thanks.
Okay, thank you very much for the nice talk. So we will take 5 minutes to exclusively ask questions about this talk, and then I will invite both of the speakers to ask questions and have discussions for both of the talks.
Let me go to an inflationary model that has really de Sitter space in the early phases. Plenty of them. Now I can compute what happens with the relative size of the tensor fluctuations. I mean, just relative size fluctuations divided by the homogeneous part of the metric. That's even a frame invariant quantity. That quantity increases when you go closer and closer to the Big Bang. Is that not going in the wrong direction, as when you say you want to start with a state that where the fluctuations do not matter? My impression is at least the tensor fluctuations, we can compute them and they get stronger and stronger. It's more the opposite, that the early universe may be fluctuation dominated.
Yeah, you must be working.
You can compute these fluctuations, of course. I mean, it's a standard computation of the tensor fluctuations, how they, the relative tensor fluctuations, how they behave when you come closer and closer to the Big Bang, and they grow.
Well, they don't grow unboundedly, right? It's h squared.
I mean, if you go further and further back, they are getting bigger and bigger. Actually, they get formally singular, the Big Bang singularity. That's part of Staropinski's argument that there should be a real singularity. There doesn't have to be one, but it's certainly an observation. Also, people who mimic, inhomogeneous cosmologies, they always find that if you go back, it gets more and more inhomogeneous.
Yeah, so that's not the case in the no boundary proposal.
So is that not in contradiction?
Oh no, not at all.
Why not?
Because you're not calculating, your story has nothing to do with the no boundary proposal.
No, but my story has to do with what we know that happens in inflationary models.
Classically, you're extrapolating classically.
Yeah, so I'm just saying, the classical extrapolation goes in a direction that is completely opposite of your assumption. You may say, of course, that suddenly breaks down or something like that, but I make just the observation that a priori, if you just look at face value, you get the impression that when you go back in the inflationary universe, it gets more and more inhomogeneous.
It's not completely in contradiction, right? When I say that the fluctuations vanish, I mean the fluctuations vanish all the way at the bottom here. This is a region where the geometry, where the background is quantum mechanical. The typical size is that of the set by the scalar potential, so it's much larger than the Planck size. There you have, but in that complex region where you do the transition and where you start inflating, you just have your classical story. Your tensor perturbations are there, your scalar fluctuations are there. All I'm saying is that the classical extrapolation backwards at some point breaks down even at the level of the background, and that's where the no boundary ingredient kicks in. And that is indeed, of course, in this very earliest phase, a huge and strong and ad hoc a priori, perhaps, regularization of what otherwise would evolve into a singular state.
Let me
I certainly agree that the no boundary proposal is a very strong theoretical ingredient or input that one puts there, sure.
Let me just, I mean, I'm not saying that there is an absolute contradiction, but it's also not true that it's just classical. The two-point function of the graviton is, of course, a quantum object as well. So even in in simple quantum gravity theories, if they produce inflationary universe, you have a two-point function in the tensor sector that goes first to larger and larger values. I'm just saying it goes in a certain sense in the wrong way for you. You have to cut that off and say, I have a proposal where the beginning is completely different and I reach first very large fluctuations and then they become smaller. You know, for simplicity, it would be simpler if you would start with a universe that is fluctuation dominated.
Also, your fluctuations start in the Bunch-Davies, right? You're assuming some sort of
But that
state.
is Bunch-Davies vacuum. The Bunch-Davies vacuum, you compute the tensor fluctuations, and they grow if you go towards
I'm doing
the
exactly
Big Bang.
sorry, but I'm doing exactly the same. Hartle-Hawking implies Bunch-Davies on the fluctuations.
Okay, more questions.
In
We
fact,
can continue.
Bunch-Davies is sometimes called the Euclidean vacuum.
Do you agree that the tensor fluctuations grow in standard computations when you go towards the Big Bang in an inflation?
Not if you put them initially in the Bunch-Davies.
Doesn't, I mean.
What you mean is something.
All these calculations, these standard calculations, start formally with Bunch-Davies. And then, of course, people say it's not valid for all the time and things like that. But there's a simple observation. If you take this standard approach, Bunch-Davies vacuum, or just invert the propagator of the effective action gives the same result. There's an observation that the tensor fluctuations grow when you go towards the Big Bang. I mean, you may agree or not agree to that, but that's the observation that everybody makes.
It's a useless discussion because we're saying exactly the same thing. You're saying the fluctuations grow when we go back to the Big Bang, and then all of a sudden, miraculously, they die to becoming the Bunch-Davies vacuum.
Your proposal.
No, that's your proposal. You also assume Bunch-Davies.
I'm saying it's much simpler if the beginning of the universe is actually fluctuation dominated and not dominated by homogeneous fields.
Then you're not
your
putting them in
proposal
Bunch-Davies.
is that it's
but then you're not putting them in Bunch-Davies.
So you are doubting that the tensor fluctuations grow when you go back? I mean, just take the standard calculations.
You're confusing classical and quantum behavior.
That's a statement about the propagator. That's not classical and quantum. I mean, the propagator is an object that exists in both. If you make a classical approximation or not.
Are you starting with Bunch-Davies or not?
I'm actually, if you do the calculation with Bunch-Davies, that goes back to Rubakov and so on,
I'm asking a yes-no question. Are you starting with Bunch-Davies or not?
I can say I start with Bunch-Davies. Actually, it's not the most elegant formulation, but...
so then we're doing the same thing, and the fluctuations will behave exactly the same. In fact, it's known
So
since
do
the
they
80s.
grow or not when you go towards the Big Bang or not in this type of inflationary cosmology? It's a very simple question. It's frame invariant. There exists plenty of calculations that find that actually the relative fluctuations grow when you go backwards, the tensor fluctuations. True or not true? early beginning, but it's just an observation.
I'm saying that in the no boundary state, the behavior of the fluctuations in inflation is just like the usual Bunch-Davies calculations.
Which gives you growing tensor fluctuations. Sorry.
So we are actually well into the discussion time, so feel free to continue if you want. Okay, so the next question. So you can now ask also, I think, maybe you can go there. You can ask your own question. Okay, so that's yours.
Can I ask my question?
Maybe after.
Okay.
I have a question for the first speaker. I think it's a continuation of the question that was asked. I had a question. You were saying that you have a universal result for complexity. And my understanding of complexity is that it's a very usually ambiguous quantity, especially in field theory, right? It's only well defined when you have a specific quantum information protocol. So could you specify? So you must be using a particular notion of complexity.
No, I'm just saying that the result is universal for a very specific state. So the state is firstly Gaussian, and so this is obviously very specific in field theory. And then I am considering a complexity between two regions which are separated by some causal horizon. And only then, for this long-range entanglement, which people have calculated the entanglement entropy corresponding to this kind of regions. And for instance, in the De Sitter case, that was computed by Maldacena and Pimentel. I'm saying that the complexity for such systems seems to be very universal in the sense that it's finite and it's independent of this Lagrangian. But this is obviously a very specific quantity. So I'm looking at a free scalar field, and then or free fermion field or something. And then also it's like a very specific Penrose diagram that I'm considering.
And you have a specific definition of what you call complexity, which I missed.
I'm using this circuit complexity, but for Gaussian states that can be defined less ambiguously, up to a cost function.
Okay, you want to continue?
I do have a question for the second speaker, Thomas, about something about the no boundary proposal. So you mentioned this Kontsevich criteria, which is in terms of the matter. But I thought, my understanding was that when you have matter, somehow there's like two possible, ways in which you need to rotate in the complex plane, depending on whether you have a lot of matter or depending on whether it's pure gravity. Could you comment on that? Like if you use, if you use or if you use the analysis of the saddle and looking at which branches you should look at. I thought you were part of that with Neil, right? You looked at this, or at least Neil Turok looked at these different. There's different type of saddles depending on the matter content. Like the different type of left-shade symbols you need to select.
Yeah, but that is more in some sort of Lorentzian kind of part integral picture,
yes.
right?
If you start from you're not.
No, I looked at this, but that's quite a while ago. I have nothing really to. What was the outcome of this whole thing? Let me think. I think Neil was looking for, or Neil was worried, right, that if you have a lot of matter, you could be picking up a different saddle in which fluctuations essentially would not be well behaved. Right. Since then, the picture has changed a little bit. So Neil was taking a kind of a path integral seriously, and he had identified an exponentially suppressed saddle, which, however, could become the dominant saddle when you had a lot of matter. Yes, exactly. But I think the lesson of holography is a little different. The no boundary proposal emerges from these DSCFT proposals, and it does so only with the usual saddle. And so I think you're gonna have to have, and this is what Neil had, a different theory of the path integral. He had the Lorentzian path integral in order to pick up those non-physical saddles or so. But this is really quite a while ago that I'm trying to remember.
So you're saying that the Lorentzian analytic continuation is kind of a
yes.
It's a different criteria than this
exactly.
Kontsevich.
So now I see
that's what.
Now I see the confusion. Yes, what I was talking about here were different representations of the usual no boundary saddle point. What Neil was talking about was contours connecting different saddle points. So he was taking some sort of path integral contour much more seriously than I was doing here.
Okay. Shudo, you wanted to ask something?
For you? Okay. Which is, so you use this different representations of the contours and did some, so that picked up this ADA space, and then you went to the CFT dual. But is this CFT dual, can you relate this to the CFT dual to de Sitter directly, like a la Maldacena? And like, for instance, for this higher spin gravity, we know what kind of CFTs are. Is there some match there?
Right, that was the key point. The crux of the statement here is that it is in fact the same ADS-CFT dual that acts as the dual in DS-CFT. So we do holography as we usually do it. And the reason that we can do this is because the connection between de Sitter and anti-de Sitter is all in the counter terms, is all in the surface terms. Now you might say, well, wait, this is too easy. And indeed, it becomes more complicated when you consider the wave function with sources turned on, in the Hartle-Hawking wave function with a scalar field turned on or whatever. Then you could play the same game. In fact, the entire Hartle-Hawking proposal can be rephrased in Euclidean ADS-CFT language. It's in fact pretty much Euclidean ADS-CFT avant la lettre. But the sources that we're interested in cosmology, real scalar fields or infradon turned on, they will eventually translate into complex sources on the ADS side. So if you think about the ABGM partition function for various sources, a la Friedman-Pouffou or whatever, we can evaluate those partition functions for real and complex values for those sources. And in ADS-CFT, we're always interested in the real values because that's what we compare with real Euclidean ADS saddle points. In DS-CFT, we're interested in complex values for those sources.
But maybe a quick follow-up is when you have the scalar field in de Sitter, there's usually like two operators which are dual to it, the two shadow operators, and that's the idea behind having this entangled two CFTs to give de Sitter. So in this picture, but for ADS, like is there like similarly like two shadow operators? Two operators like this of dimension.
Oh, I see. I hadn't understood that's what you were doing. You're saying your left-right thing, right?
Yeah.
And you're saying that somehow the quantization condition is different on the left and the right? You choose a different...
Yeah, just like the H plus and H...
Yeah. Oh, I see. Okay.
Is there something similar which emerges naturally?
Okay, yeah, so of course I wondered about that in your talk as well. I don't immediately see it in the sense that if I were to evaluate my wave function of the universe in position space, then evidently it would be the slowest fall of that provides the argument of the wave function. Of course, I could be inclined to evaluate the wave function in momentum space, and then I probably would have to select the other thing. But we do not have this left-right thing. If anything, in this version of DS-CFT, the analog of the wormholes in ADS or the entanglement or whatever would rather have to do with the scry minus and scry plus.
Okay.
You see, we always have two saddle points and they come in complex conjugate pairs, and how are they connected? That is a tricky question.
I see. Okay. Thank you.
More questions?
Okay, for Thomas, just to clarify your results, if I take, say, my inflationary potential as m squared phi squared, for example, Are you saying that's just forbidden by your underlying principles, or is it just that it's allowed but the prediction moved down in the NSR plane?
I'm saying right, if you were to fix the overall amplitude, then indeed it's ruled out. You don't get these 60 e-folds with this additional Kontsevich-Segal criterion applied to the saddle. Yes.
Okay, so it's sort of a sick theory in some sense, in your point of view.
Well, I applied this criterion just because I was curious, right? I'm not saying I understand what it does, but it's very fascinating because this Euclidean-Lorentzian transition goes exponentially fast, essentially. They're exponentially small corrections to this Lorentzian background, and somehow this criterion picks that up and appears sensitive to what these precisely are. So it's clearly some sort of non-perturbative quantum gravity effect that the criterion captures. But why now m squared, phi squared not, and the others yes? People familiar with the swampland program in string theory may have noticed some sort of connection between these results and what the swampland criteria tell us. Both sort of zoom in on concave patches of the slow roll potential. So that's, to me, the interesting thing happening here, that somehow this Euclidean quantum gravity framework, semi-classically, and swampland reasoning, completely different, seem to point to the same thing. There's clearly something to be understood there.
If I can just ask one related thing. So if I tried doing, say, m squared phi squared for phi a few m Planck during regular slow roll inflation, and then declared that the phi squared shape flattened or did something else, does it then obey these principles, or is it still forbidden?
Yes. No, then it will obey. Yes. So it's very sensitive. So it sort of connects the earliest phase, almost literally the no boundary Euclidean phase, and the late time behavior. That's what the criterion magically connects. And so if you change one, you will indeed,
More questions?
It's too bad that we come to this prediction now and not 10 years ago.
We still have some time, so don't be shy.
I guess we can be also slightly provocative. So, wouldn't you agree with the following statement that, okay, this Niels program or whatever, I mean, Neil was just one of the followers, by using Lorentzian signature in the path integral should be what we mean by the definition of quantum gravity, and anything else should be an approximation, and maybe these Euclidean and these, Timballs and whatever, the saddle points that dominate the contributions, which obviously is along this Euclidean path, should be sort of telling us if you Euclideanize gravity, how much actually we can trust and how much we cannot. I'll just give you an example. I'm pretty sure if I do Lorentzian path integral on finite time interval, then the Euclidean approximation will have corrections to it that I can calculate. So do you have any comment on that?
Yeah, sure. I think that's right. Ultimately, the discussion with Neil a few years ago boiled down to a fundamentally different assumption on what's fundamental. He was taking the Lorentzian path integral very seriously, also for the cosmological problem, including the Big Bang. And we were taking the Euclidean viewpoint seriously as a starting point, motivated by DSCFT and holographic statements. And And evidently, the debate really is, yeah, what do you do at the Big Bang? Do you close the past, or do you put an initial boundary? It's a little bit like that. Of course, the Lorentzian path integral is fine if you go from an initial boundary to a final boundary. This was, however, not the problem we were trying to solve.
Yeah, but I mean, don't you think that quantum mechanics tells us that there is a phenomenon of interference, just even for single particles, and that the laws of quantum mechanics are those, and observations are those that support these phenomena of interference, and unless I change rules of quantization in gravity, I somehow expect that the same phenomenon.
No, not at all.
No?
Usual quantum field theory comes out of this, of the Hartle-Hawking construction, right?
Yeah, but not
once you have a background and you have a notion of time, it's all the Schrödinger equation comes out.
Yeah, but only the low energy part. I mean,
sure.
Not all the excited states.
Sure.
I mean, not all of the structure.
All of the structure, as long as you have a classical background, which is what you're assuming. A classical space-time.
Yes.
Yeah. Everything else comes everything else comes out. It's only when you're talking about having no classical space-time that Hartle-Hawking begins to differ from anything normal.
Okay.
Sure, you can have black holes.
Black holes, when you get close to the singularity, you don't expect to.
Well, that of course.
That you can do the this mini superspace model. This looks.
Sure, that's a very interesting question, of course.
Highly. No, but I'm surprised that. In this Euclidean approach, you use mini superspace model. You don't need to do the full path integral. And this is surprising that with this very sort of simple model, you're able to recover. The question is, what would happen if somebody would go ahead and do the full path integral, let's say triangulations or something like that?
Well, yes and no, right? If when I was comparing the quantum corrections to the de Sitter entropy, which we were getting from the dual field theory, so in principle that is the full answer. When I wanted to redo that calculation on the gravitational side, working with the Euclidean saddle point, I had to include a higher derivative correction to GR, and I had to calculate loop corrections. So if you're gonna move beyond the semi-classical approximation, you're gonna have to include a lot of baggage. We were up there we were in 11 dimensions and everything, right? No, it doesn't remain just.
Let's say you stay in 4 dimensions. Let's say you don't.
Then there's a limited number of things you can derive.
I mean, you can do Reggie calculus, take triangulation, sure. And but then it's amazing that even in a Euclidean space, you just sufficient just to take the mini superspace model to give you more or less.
Yeah. So this goes back to the.
Although the question of black holes, I think you won't be able to play this game if you want to explain what's going on with the black hole. I think there you really need to do the full path integral.
Well, even there in the low D models, people have now, as you know, have found wormhole saddles that could become relevant after the page time and all that. In the last couple of years, the Euclidean quantum gravity framework seems to deliver there exactly where you don't think it should be delivering. Why? I don't know. It seems to hold certain non-perturbative corrections to gravity in a fairly.
I mean, you're expecting to have a huge fluctuations in the regions of large curvature.
Sure.
So
Sure. It doesn't do that.
This sort of
no, I agree with that.
Small fluctuations should work.
So sure. Sure. Yes. The end of time could be very different from the beginning of time.
Or locally, if you're in a black, you go toward the curvature singularity.
Okay, so I don't see any other questions, and we are at the end of the session. So before you leave, we have one announcement, but before that, let's thank the speakers and our technician.
Yeah, so short announcement now that you've got a taste of discussion. On Friday afternoon, the closing of this conference will be a nice panel consisting of quite a broad range of expertise, I would say. Bianca Dietrich, Renate Lol, Steve Carlip, Steve Giddings, and Jan de Boer. So we're collecting questions, themes, topics to discuss during this panel. So if you have any ideas about the common themes that have emerged during this conference, or questions about where quantum gravity will or should go in the next couple of years, then please put them in the Google form link that we sent around yesterday morning. We'll send it around again later tonight. Okay? So any question is much appreciated. And then see you tomorrow at 9.